Right. Good morning, every one of you. We will start the reverse class. Right. I will take only few minutes to explain the benefit of a reverse class like this. Through the reverse class, we try to complete the last few lessons in advance. That's the simple story. We try our best to complete the last few lessons in advance along with your normal classes. So you get the chance to complete the whole syllabus in advance, right? So what are the benefits then you have after completing your syllabus in advance? There are a lot of benefits. Simply, you can do model papers which consist with whole syllabus, where you don't get that chance normally because the syllabus completed at the last moment. Normally, a topic like mechanical properties of matter, that section completed at the last moment. So the student don't have time to complete them. I mean, complete them properly, and they don't have time to do questions. So today we'll be starting mechanical properties of matter. We'll complete it within 3 consecutive days. So you get the chance to do questions on the mechanical properties of matter because you know that part clearly. That's one of the great advantage that you get. Not only that, when you go close to your exam, I mean when the exam is too close to you, you are with a certain pressure if your syllabus is not completed. You are trying to complete the syllabus, but that there are several sections to be completed, and you are in a pressure how to complete those sections. So that issue also not there. So you can freely face the exam. That stress is not there. That's another important point. And you get the chance to practice many questions under several topics in advance because we complete those sections, right? We complete those sections. And also from the last lessons, like mechanical properties of matter, the rest of the sections are also the same. They are easy to score at the exam. They are not difficult. The reason behind that, there may be several reasons. One of them is these sections normally would not cover properly with the fresh students who are doing their A level in the first attempt. Those sections are not completed properly. So because of that reason, the students are not trying for those questions. For oscillation waves question, definitely the student would try because all of them would complete those sections before the exam. But for the last lessons, those sections are not completed properly. So the students are not engaged with the reverse class. I mean, not engaged with those questions properly. What happened ultimately, the students are not trying those questions at the exam. So the people who are preparing these papers, they feel that the students don't have much idea, so they are not making that much difficult questions under this part. That's another advantage. If you look at that these questions if you analyze this part, you can understand that kind of thing also, right? If you take last few lessons, there are definitely essay questions from each topic. If I go with the mechanical properties of matter, which we will be starting right now, definitely there will be essay questions. Definitely there will be essay question. There is a tendency to give structured questions also, but I can't exactly tell you like thermal physics. I can't exactly tell you they will provide it. So there's a possibility. To take the MCQs, there are 4-5 MCQs every year under this topic. So you get this chance to complete these sections in advance. So those are the things that I want to emphasize related to the reverse class in advance. So you need to know the benefit of doing this reverse class. Even it's not easy for me to do the reverse class with you with the busy schedule I have, but I could manage to complete, I could manage to start this part because I know that how it is benefit for the students like you all. So we had the same issue when we are doing A levels because we don't have time to complete. We didn't have the time to complete most of the section in the last part of the subject. And those are few things among lot of sections that you need to know under the reverse class. The reverse class recordings would not provide it for you all. We'll request you to join the live class for the theory students. The reverse class is totally free. No need to pay any additional amount. You can get free of charge. But when you do something like free, the student don't have much value for that. So I'm not arranging you the recording for the students who are engaged with theory class. If you want, you can pay the extra amount for the recording and get it there. For the reverse class, there are a few new students who are only joined for the reverse class. You get that facility to watch the recordings, right? Watch the recording, no problem. We'll arrange you. For the theory class students, if you want, you need to pay the additional amount. I mean, it is not for me, but for the developer, there are some like 500 rupees for every students to arrange the recording. So you need to pay that amount. It is not a massive amount, but if I make it like free of charge by like absorbing that cost to me, that cost to the teacher, the student would have value for that. That's why I'm telling you, I'm not arranging you like it's free of charge. Okay. If you are joining the live class, no problem. You can get everything free of charge. So I encourage you all to join the live class. That's another reason behind this part. Behind this part. Okay. Okay, let us start our topic. Today we'll start the mechanical properties of matter. I hope you received two tutorials by now. You received two tutorials. One is this, another one is this. Okay, there are two tutorials. One is for this one is for the notes, and this one for the questions. Okay, the whole lessons that we all are coming under the reverse class will be conducted like the same way that I'm doing here. The notes tutorial plus the tutorial. So you can use this particular tute to complete your notes properly. Okay. What is the mechanical properties of matter? I think you can understand how it is important for your A-level exam. There will be one essay question. The structure is possible. There are 5 practicals that we need to discuss under the mechanical properties of matter. So that means there's a possibility of giving a structured question based on this. That's another point. MCQs 4, 5 MCQs, like 3, 4, 5 MCQs every year, they will allocate. They allocated in the exam. So that's the important point. If definitely you would get a essay question, that is not a difficult question anyway. Okay, right. The next important point, when you take the mechanical properties of matter, that is your 10th topic in your syllabus, it is mainly divided into 3 sections: elasticity, viscosity, and surface tension. Elasticity, viscosity, surface tension. Elasticity section I'll be completed today. I hope I can complete it. Viscosity next week, the surface tension next week or the other week, right? That is how the things are developed. That is how the things are planned. I hope I can do the way that I have already planned. There may be another extra week to do questions with you, discuss questions with you, maybe some difficult questions. There will be another week, but anyway, you can understand the whole lesson completed within 3 days, 3 days or 4 days maximum. Right? After that, we'll start the new lesson. That is how the reverse class is conducted. Okay. Uh, okay. We will move to the topic now. The mechanical properties of matter. In King's time, give me a second. Right. In King's time, there is no problem with the material. I mean, there are excessive material, no problems. I mean, the materials are available everywhere. If you want, if you go to Anuradhapura, Polonnaruwa, whatever the places, they develop, uh, roofs and the walls like the on top of a wall, the river water can travel, isn't it? Are you doing that same thing in these days? You are not doing these sections now. The reason is the materials are scarce. Materials very limited resources. In King's time, there is no problem. If you look at a wall, right, like King's Palace or whatever the place, they're like very large. The wall is very big. So even a demo butter can travel on it. Demo butter to not take yanna pulva, right? So if you want to use a raptor to a to a roof, they would cut a tree and make like raptors because the resources are available everywhere. The trees are there, the resources are available. No problem with that. If you have resources, even you also feel that what's the point of like limiting them. But with the development, the resources are limited. So they have developed, since the resources are limited, we will use only for the requirements. We use only for the requirement. If you want to develop a column, we are not taking a roof, we are not taking a tree. Either of that, we take only a small section of a timber part. Neither. That is decided by the structural engineers. That is decided by the structural engineers. If you want to make a column, concrete column, there must be some kind of mathematical modeling. So based on that, you develop only that part. You are not going to have more details. We only require we only do calculation and find what is the cross section that we need to use for this column. Right? We need to use that for the columns. Okay, we are not using more than that because the resources are not available freely. Cost. With the cost. Everything depends on the cost now. Everything depends on the cost. In the King's time, there is no problem. The resources are available. කෙනෙක්ට වහලයකට පරාලයක් වගේ එකක් දාන්න ඕන නම් රැප් එකක් දාන්න ඕන නම් ගහක් කපලා දානවාද ගස් ඕන තරම් තිබ්බා. දැන් එහෙම නැහැ. දැන් එහෙම නැහැ. ගස් කපලා පරාලයක් දාන්නේ නැහනේ. ගහක් කපලා පරාල කීපයක් දානවා නේ. You are doing like you are using that tree to get the maximum benefit of it because the resources are limited. That is why something called the material science is developed in this era. The material science is one of the very important topic. Material science, right? Material science. I mean, material and medicine combination is called what? Biomedical engineering. Biomedical engineering. Material plus the medicine. The combination is called biomedical engineering. Right? Biomedical engineering, where I think you know this one, the one of the best universities in South Asia, even in the Asian countries, among the Asian countries, is where? Can anyone tell me where it is the? Yeah, it is in Peradeniya. It is in Peradeniya. It is the one of the best universities in this Asia, in this South Asia country, among South Asian countries. Peradeniya University, you have biomedical engineering department. It's one of the best places. If you remember, during the COVID time, the ventilators were repaired there. Everything is done. Even the mask, they made a new mask. So those things done in Peradeniya University, one of the best universities for the biomedical engineering, right? Why I'm telling these things? The material science, it's important subject. Since you all are like the A-level students, you should have kind of opening, the eye-opening point for those subject areas, right? Biomedical engineering. So those are the location where, like, let's say now the experiments are done. Let's say let's say someone can't see anything, right? If they can't see anything, there's a electronic spectacles. What they are doing, they take electronic spectacles and ask them to wear, and they develop a kind of signal. Let's say that person is looking at some object. So what they are doing, based on the electronic spectacles, they develop that required signal, because everything depends on the signals. No? Everything depends on the signals. They develop that kind of signals. Let's say I'm watching at this. Let's say I'm watching at this air conditioner. Maybe they are, when you look at the air conditioner, there the signal is developed, right? Everything depends on the signals. What they are doing, they using by using these spectacles, they develop the required signal. They develop the required signal and send it through optic nerve to our brain. So the brain identify this as the air conditioned machine. So simply I told you, simply I'm telling you this. Huh? That is how the people can now, the most people that now then they can see the things. That is actually biomedical engineering, right? Biomedical engineering. And even the artificial name, Krutima Danissa. Krutima Danissat ඒ වගේ එකක් තමයි. Krutima Danissa කියන එක දන්නවද නේද? හුඟක් අය අම්මලා තාත්තලාට වයසට ගියාම එයාලගේ ධනිස්ස රිප්ලේස් කරනවා සමහර කට්ටිය. ඒක ඒක තමයි බයෝමෙඩිකල් ඉංජිනේරින් පාර්ට් එකක් ඒක. ඒක සර්ජන් කෙනෙක් මෙඩිසින් විතරක් දන්න කෙනෙක්ට ඒක කරන්න බෑ ඇත්තටම. There must be some kind of knowledge related to the materials, right? Material science is a big subject. Why I am telling these sections? Because we are discussing about the mechanical properties of matter. That's why I am discussing these sections. Another thing I can tell you, normally there may be some vehicles like when you drive like 100,000 kilometers, definitely there will be some kind of engine repair. There can be some kind of engine repair, but some vehicles are there. I mean, German vehicles, like European vehicles, the Benz, the Porsche, or those kind of vehicles, they can run more than 500,000 kilometers, 500,000 kilometers without any oil, without any repair. How it happens? That is the beauty of the material that they are using, right? If you take Indian car, I'm not criticizing any country, right? If you take Indian car, the Chinese car, probably we have to do some repairs after like 1,000 kilometers, maybe 100,000 kilometers. But those vehicles, even you can run over more than 500,000 kilometers without any repair. What's the beauty of that? The beauty is the material that they use, right? Material that they use. If you take a jumbo jet, they take and strike on the ground. The whole weight is now tolerated by the two plus another two tires, jumbo jet. But if you do that, if I stand and do the same thing, like I take my car to a rock and do that path, can you think that what will happen? Can you think what will happen? You can imagine what is happening there. You can't do that part. But jumbo jet is a very massive mass. It is only that massive mass only tolerated by those small tires. That is why the materials are so important. They use different types of material for those tires. In normal car, we are not supposed to take that kind of jump. No, it is not required to do that way. But anyway, you can't do even. So they use different tires, different types of tires. So what I want to tell you is this: the material science is very important point in present day situation. Material science, very important part, right? And biomedical engineering is another part that if you want, you can try for that. It's a very important part for most of the students. Biomedical engineering, it's a very important part. It's a combination of medicine and material science. Right. Okay. Let's move to our main topic, elasticity. Elasticity. Can you take our tutorial, the page number 2, this one, okay? Page number 1, unit number 10. I have given the new number 10, mechanical properties of matter. Mechanical properties of matter. Mechanical properties of matter. Properties of mechanical properties of matter section is divided in 3 sections. Number 1, elasticity. Elasticity. Number 1, elasticity. Number 2, viscosity. Viscosity. Number 3, surface tension. Number 3, surface tension. Number 1, elasticity. Number 2, viscosity. Number 3, surface tension. Right. I will explain what is meant by elasticity. Pay your attention to this. We will move to that part. Right. Let me take this kind of spring. This kind of spring. It's a spring. Right. So I just pull this spring in both sides. You take this a certain force on it, let's say F, and let's say F. Imagine what will happen. Now you have a rubber balloon like this, which is closed, the opening, rubber balloon like this, and you apply certain force on it. Based on that force, the volume or the shape would change. Volume or the shape would change. Now you have a clay sample on top of a table. If you apply a certain force on it, what will happen? The shape would change definitely. Let's say you have a certain metal rod on top of the two stands. Metal rod. If you apply a certain force at the middle, we could see that the metal rod become this kind of bend. Example number 1, example number 2, example number 3, number 4. These are 4 examples. The spring which is pulling at the 2 ends, balloon which applies certain force on it, and the clay sample which applies certain force. Think what will happen then. There is a metal bar. When you apply a certain force at the middle, what will happen? It gives kind of bend like this. If you take the first instant and the second instant, if you release the force, what will happen? If you release the force, what is our observation? They would come to the original shape. They would come to original shape again. No problem with that. They would come definitely to the original shape. When you apply certain force and release it, they would come to original shape. But third and the fourth example, this is the clay sample and this is a rod, metal rod. When you apply certain force, what will happen? There is a permanent deformation. The clay sample would reach up to this point, and this bend also make permanent situations. So that is important point. There are some properties in materials. When you give a deformation, the change in the shape or the volume is called the deformation. When you change a shape or the volume of it, we call it deformation. By applying a certain force, you can give a deformation, isn't it? You can do the deformation, you can give the deformation. But what will happen if it is release the applied force? When you apply the force, what will happen? The deformation is not there. Those two materials, we could see they would come to the original shape again, while these two are not come to the original shape. So if the material comes to its original shape again, this property is known as the elasticity. We call it elasticity, elastic behavior, elasticity or elastic behavior. Those materials are called elastic materials. Elastic material, normally most of the time the metal, rubber, they are elastic materials. There are some material where you don't have that property. Then they are called inelastic material. Inelastic material. Okay, right. I think you all are clear with this. Just move to our topic. Come to our note. Each object change its shape or the volume due to an external force. Due to an external force. By applying the pulling force, we can increase the length of the spring. Right? Draw this. I will read the other part also. By applying a force onto a balloon, we can change the shape of the balloon. By applying a certain force, we can change the shape of the clay contained. By applying a certain force to the metal rod, we can change the shape of the metal rod. Shall we draw those four examples? Shall we draw those four figures in the space provided? තම ඔයාලට කියන්න දරුවෝ මේ ලෙසන් එක හොඳටම ගොඩ දාගෙන මේක ඔයාට පුළුවන් කරගන්න ඕන. මේක මේකෙන් ආවොත් ඔයා ක්වෙස්චන්ස් කරනවා කියන බේස් එකට ගන්න. ඒකට හරියම ලේසි. ඒ නිසා මම කියන්නේ මේ ලෙසන් එක ලේසි. නැත්තම් මට මේක දවස් 4කින් නැත්තම් 3කින් ඉවර කරන්න බෑ කියන එක ක්ලියර් නේ ඔයාලට. අමාරු නම් මේක කරන්න බෑනේ මේ විදිහට. එතකොට දැන් අපි mechanics වගේ ගත්තොත් දවස් කොච්චරනම් කළාද මාස කොච්චර කළාද even when you take the oscillation waves thermal physics how many months we completed those sections we take to complete even thermal physics we have some more things to do it is not over but these sections are like very easy to score right now come to it again after removing done right okay this take a note. After removing the applied force, the spring and the balloon come back to its original shape, but the third and the fourth object do not. In the case of certain substances, when the force is applied, they change the size or the shape temporarily, or both. But after removing the applied force, the object will come back to the original size and the shape. This is known as the elastic behavior. This is known as the elastic behavior. The material which shows the elastic behaviors are known as elastic material and the other materials are known as inelastic materials. Right? Inelastic materials. Example for elastic material. Right under that. Rubber, 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 comma, metals, most of the metals. Example for inelastic material, clay, clay. Right. Deformation. We'll move to deformation. What is deformation? We will start. Right. So deformation means anything that when you apply certain force on it, just change the shape of the volume. That is called the deformation. If you apply certain force onto a certain substance, its volume or the shape would change. No, volume or the shape would change. That is what we call the deformation. Neither. That's what we call the deformation. Mainly, there are three types of deformation. Three types of deformation: one-dimensional deformation, two-dimensional deformation, three-dimensional deformation. Okay, let's say you have a spring like this and you apply certain force. If you want, you can say it is fixed at this point. You apply certain force. When you apply certain force, the length would increase. Length would increase. It is actually one-dimensional deformation. Only the length would increase. Length is only the point. Length would increase. Here, if you take a rubber lamina, lamina means something like this, The thickness is very small. That's what we call the lamina. Rubber lamina. Rubber balloon එකක අර පිපුරුනහම තියෙන කෑල්ලක් කියලා හිතන්නකෝ. Rubber lamina. Right? When you apply certain force on it, like this, what will happen? The area would change. The length and the width both are changing. Actually, that is called the two-dimensional deformation. Two-dimensional deformation. Understood? Now, let us take another instance. Right? So let's say the sponge. Sponge. You know the sponge? I hope you know the sponge, right? So when you squeeze the sponge, the volume of it would change. The shape would change. That is called the three-dimensional. All the length, width, and the height would change. That is called three-dimensional deformation. So every direction you do it, what happened finally? The shape would change. The volume would change like this. It is called three-dimensional deformation. There are three types of deformation. Okay. Shall we complete the note? Deformation. Just write under that. Change in the shape of an object. Change in the shape of an object. Change in the shape of an object. Change in the shape of an object due to external force. Due to an external force. Due to an external force. Due to an external force is known as deformation. Is known as deformation. Is known as deformation. The rest of the part is given. Deformation in elastic materials are known as elastic deformation. Right? Elastic deformation. All these three materials are elastic materials. The deformation on those three, on elastic materials are called the elastic deformation. Deformation in elastic materials are known as elastic deformation. Deformation in inelastic materials are known as inelastic material. Inelastic deformation. Deformation in a material can be observed in three different ways. One-dimensional deformation, right under that. Increase in the length of a spring. Increase in the length of a spring. Increasing in the length of a spring within bracket rubber cord or rubber strip, close the bracket, rubber strip. By applying, by applying, by applying, by applying pulling force, by applying pulling force at the two ends, at the two ends, by applying pulling force at the two ends. Right. Shall we draw that? According to the note, it is given as this by applying pulling force at the two ends. No, sorry, let's make like this. Right. Two-dimensional deformation. Right under that, increasing the area, increasing the area, increasing the area of a rubber strip, sorry, rubber lamina, of a rubber lamina, increasing the area of a rubber lamina due to application of forces, due to application of forces, due to application of forces. Right. Do this. Right. Three-dimensional deformation, volume of a sponge, volume of a sponge, volume of a sponge, change due to forces, change due to forces, volume of a sponge, change due to forces. Right. Okay, pay your attention to this now. If you analyze how and why this kind of thing is happening, I mean, when you apply certain force and when you release it, it comes to the original position. Why is that? Under the elastic material, we can analyze in, based on their atomic behaviors. Atomic behaviors. For those materials, Lama, if I take a rubber strips, if I take a rubber strips like this, let's draw like that. If you take a rubber strips like this, let's take the intersection of that, I mean cross section of that. If you take a cross section like this, we can analyze inside this material, these are atoms, maybe molecules, atoms. Inside these materials, they are having some kind of interatomic bonds. They are having some kind of interatomic bonds. These are interatomic bonds. Like a spring. Okay. Right. What will happen if I take this part only? What will happen if you apply certain force on it? And this end also you should apply the same force to give the deformation. right? Okay. So if you apply certain force on it, what will happen? The interatomic distance between the two atoms would change. Between the distance between the two atoms would change. For example, if I take this cross section, the distance between the two atoms would change. For elastic materials, there's a own property. When the distance is high, they try to maintain the original length, original distance. When they increase their length, when they increase the distance between those two, what will happen? They try to develop, they try to come to the initial locations. Based on that, the forces are developed. The forces are developed. Actually, when you try to increase the length by applying certain force at the other end, F and F, what will happen? The internally, if I take this cross section, internally they would develop. They try to develop. They try to come to the original position again. So the forces are developed. Forces are developed. Now now the new distance is more than the original distance. Earlier it was, let's assume these are the 2 points now. Earlier, now the distance is high. They would come to develop, they would come to original distance. To come to the original distance, they develop their own forces. If I take the certain cross section, you can see these develop a resultant force. These forces would added together because they are having the same distance, same direction. They develop the resultant force. At the beginning, when you apply certain force, these values are not so significant, but when you increase the length further, these forces become significant. At a one stage, these are called elastic forces. These are called elastic forces. Okay. These are called elastic forces. At a one instant, what will happen? These resultant of one, if I take a one cross section, the resultant of these elastic forces would equal to the applied external force. At that moment, no extension would take place further. Stop there, right? Even if you take a rubber strips, let me take a rubber strips and explain. If you take a rubber strip like this, so at the beginning, the original length is this. Now I'm increasing this. When I'm increasing the length of it, what's happening is I'm explaining now. When I apply certain force, if the force applied is fixed, at a one stage, it is no longer given extension, isn't it? What happened actually? Inside resultant is equal to outside resultant. That's the reason. Otherwise, so you keep on length increasing, no, that won't happen. So these are called elastic forces, right? Elastic forces. If you can imagine the resultant, if it is an equilibrium position, the resultant of these forces must be equal to the external force, right? External force. If I take this area, this cross-section area as A, cross-section area as A, now the external force and the internal resultant, which is called the elastic force, is equal now. So F over A is called the stress. We call it stress. F over A is called the stress. Sigma. We call it stress. We call it stress. But remember, stress, for the stress, we need elastic force. But however, elastic force is equal to the external force. Right? This is the same thing I can explain if you give a compression. If you try to give a compression, for example, let's say you have a rod like this. You have a rubber rod like this. You give a kind of force on it. Because of this force, That's a compression. When you have a compression, what will happen? The distance between the two particles, two atoms, now less than the original length. Less than the original length. So what will happen? They develop some kind of opposing force for that. And finally, they come to the equilibrium point, normal position. At this point, you can imagine the same concept is there. The same concept is there. If you want, you can take an area as A. F over A is equal to this answer again, stress. This is the same force. At this point, actually, at this point, if an internal resultant is equal, like cross section, to take a cross section, they are the same, right? They are the same. This is the internally what happened inside the elastic material. That is what I am trying to discuss here. Internally, they try to bring them back. They try to bring them back. The result of one side is equal to F. The result of one side. Try to understand. Okay, these are very simple things. Try to understand. Okay. Right. Shall we complete the note? Elastic behavior of matter. Elastic behavior of matter. Let's consider a rubber strip which is pulled in opposite ends. In a solid, each atom or molecules surrounded by neighboring atoms or molecules. These are bonded by interatomic or intermolecular forces. Where a solid is deformed, the atoms of the molecules are displaced from their equilibrium positions, causing change in the interatomic distances. Right. Okay. Shall we draw these two here? Don't write this, huh? Don't write this, just do that. Are there any new students? I mean, are there students who are joining for the reverse class only? Right, okay, there are a few. Ne? Did you get the tutorial? I mean, did you get the hard copies? To your home? Right, done. Let's move on to the note. Interatomic forces tend to drive them back to the original position. These are called interatomic forces. Drive them back to the original positions. At the start, the resultant of all those forces, which is through a cross section, is less than the applied force. At the start, maybe if at the start, when I started to apply certain force, I should keep on increasing this force until the certain value is reached. No, if I apply neither, you can understand. No, at this point, if they are at the original length, the applied force is 0. Now apply 1 Newton, now 2 Newton, 3 Newton, 4 Newton, 5 Newton, like that. Up to 5 Newton, I apply. Okay. So at the beginning, you don't apply any force. Original length is maintaining. At this point, the resultant of those values will be 0. That's what I'm telling. It is 0 value, no extra value. But when you increase it further, 1, 2, 3, 4, 5, this also keep on increasing because the length would now deform, and length would increase. At one stage, this whole value would be equal to 5 Newton, which is equal to 5 Newton. Right? Right. But owing to further extension, the resultant force increases and at a certain stage it is equal to the applied force. When this occurs, the material has the maximum extension, deformation due to external force. When the external force is removed, elastic force inside the material will bring it back to the original form. If you release this F, internally you have the elastic force, bring them back to the original length or the original situation. Okay, let's move on to the one question is there that sir, is it similar to how static friction varies with the applied force? So we will discuss how the things are developed. We will be discuss how this elastic force would develop with the external force. Nothing to worry. We will move to that part. Another few minutes later, we will move to that part. Okay. Right. We will move to stress now. The stress for a material, like for elastic material, the force is not so important term, I must say. Elastic force is not so important term. Instead of that, the stress is one of the important point. The stress. Because we all are discussing about the material science. Ultimately, we should have an understanding what is important for a material. It is the stress. It is the stress. Let's say, uh, there's a man. There's a man, right? You give him a shot. There's a man. You give him a shot. Think about that. And the next situation, you give him a shot using your finger. You are giving the same amount of force, but the affected area is very small. You give a slap on this man. Think about that value. And next attempt, you give the same force, but using your finger. This area, affected area, is very small compared with the previous one. In the next instant, you take a needle and do the same thing. What will happen? What will happen? You can understand at the last moment the needle point is very, very dangerous. Right? That the man get very pain compared to the previous two instances. Isn't it? The considerable pain is developed. This for the material, the stress is more important term than the applied force, more important term than the elastic force. That is why I want to emphasize stress. If you take if you take if you take your leg, this is the shape of that now. It is not exactly shape. This kind of shape is maintaining now, right? If you take a point like this, if the muscles behavior, muscles, the muscles shape and the muscles shape at the same or different. A point like this and the point like this, they are different. You can understand the total weight is tolerated by this leg. If you stand using one leg, let's assume that the total weight of this man is balanced by this balanced by what? Balanced by this leg. So the total weight and the reaction resultant apply along this leg. Think about the forces developed within this unit, within this small area. A considerable force is developed. This when it comes to this point, the force is not so strong. I mean, the same force but large area. If you take a point like this, the force is the same but a large area. Compare with that. So the muscles at this point is much stronger to absorb that force, absorb that stress, not the force, stress. The material of this, if I go with the materials, material of this, material of that, I mean, the patterns are not same. That's what I would tell you. The patterns of these muscles are not same. The anatomy of these muscles are not same. That's what I want to tell you. Did you get my point? මේ පැත්ත ටිකක් strong විදියට තමයි මේ muscles තියෙන්නේ. ඒක hard වල අල්ලුවම තියෙන hard. හැබැයි මේවා soft. මේ location තවත් soft. ඒකට හේතුව තමයි මෙන්න මේ stress එක. වා එකම force එක යන්නේ මේ force එක යන්නේ R එකම force එක resultant එක normal reaction එක F එකමයි හැබැයි affected areas වෙනස් වෙනකොට මෙතනදී පොඩි area එකක් තියෙන්නේ. එතකොට stress එක ගොඩක් වැඩි. stress එක ගොඩක් වැඩි. stress එක tolerate කරගන්න මේ muscles හදා ගන්න වෙන විදිහකට muscles හදා ගන්න වෙන විදිහකට මේ වගේ තැනකට එනකොට මෙතන area එක ටිකක් වැඩි. එතකොට stress එක අඩුයි. එතකොට මේ වගේ muscles තිබ්බාම හොඳයි relax වෙලා ඉන්න. ඒක මම මේ කියන්නේ material science. මේ වගේ තැනකට එනකොට area එක තවත් වැඩි, stress එක තවත් අඩුයි. එතකොට මේ වගේ තැනක ඔයාලට තේරෙනවා නිකන් අර ගැහුවාමත් නිකන් muscles ඔහම vibrate වෙනවා. හැබැයි ඔයාගේ කකුලේ මේ වගේ තැනකට ගැහුවාම එහෙම vibrate වෙනවද? එහෙම වෙන්නේ නැහැ. එහෙම වෙන්නේ නැහැ. ඒක තමයි කියන්නේ. ඒ කියන්නේ material කියන එක හරියම important topic එකක් අපේ life එකේ පවා. එක එක instant වල එක එක locations වලට දෙයියෝ දීලා තියෙන දෙයියෝ දීලා තියෙන pattern එක වෙනස්. කවරේ මාවපු කෙනා දීලා තියෙන එක වෙනස්. ඒක වෙනස් එකක්. එක එක locations වලට වෙනස් විදිහට තමයි ඒක තියෙන්නේ. එහෙම නොවුනනම් අපිට survive වෙන්න බැරි වෙනවා. I think you have completed those two figures නේ? නේද? හරිනේ? Okay. What is stress then? Stress is simply the elastic force divided by the area. Just write under that. When the body is subject, it's given a stress. When the body is subjected to external force, an elastic force is developed in the body. That's what we call when you subject to external force, elastic forces are developed inside the body. This elastic force is equal in magnitude but opposite in direction to the applied force. This elastic force is equally opposite but opposite to the direction of applied force. Right under that. The elastic force per unit area. The elastic force per unit area. The elastic force per unit area. Elastic force per unit area. Elastic force per unit area is called the stress. Is called the stress. Elastic force per unit area is called the stress. Elastic force per unit area is called the stress. If F is the force applied and A is the area of cross section of the body, magnitude of the stress equal F over A. Right, sigma. Sigma, the symbol is called sigma. It is equal F over A. Unit of sigma. It is the pressure unit, Newton per meter square. Newton per meter square. Sigma, stress, Newton per meter square. Dimension of sigma, it is the same dimension as the pressure, ml minus 1, P minus 2. Stress. Right, done. Then there will be another important topic called the strain. Strain. The strain is another important topic. I will start like this, then you can understand. Let's say you have a certain length, let's say 1 meter length. You have a same material, the same cross section, everything is the same. Only thing is you have 2 meter length. If you apply the same force F, if you apply same force F and F, if the final result is the same, if this final result is the same, imagine what kind of a length would increase. Both are in the same location. Imagine what kind of a length would increase here. Imagine what kind of a length would increase at this position, 2 meter one. Which one you feel large? Is the same or large? 2 meter, definitely 2 meter would large. 2 meter would large. So here, the strain is not simply the stress. I mean, not simply the extension. It is defined, it is considered based on the original measurement. The strain is epsilon. It is normally denoted as epsilon. If you apply F force, there may be some kind of length increase. The new length would be, let's say, the new length is something like, the new length is E1. If you do it for the 2 meter, it is definitely more than E1. E2 is greater than E1, isn't it? E2 is greater than E1, more than that. So that means based on the original length, extension would differ. So the strain is defined as the change in length or the change in measurement divided by original measurement. Original measurement. Epsilon be equal, for this case, it is E1 over 1 meter or E2 over 1 meter. If you go with the general case, E divided by L. L is the original length. Sometimes you might feel that why we all concerned about the length increase, the area also increase, volume also increase, why we don't want to think about that volume increase, the area increase. Yeah, that also accepted. Area would increase, the volume also increase or decrease, depending on the situation. But in this particular lesson, we only concern about the length increase. We are not taking the area increase here. Area or the volume increase. We take only length increase. Right? Throughout this lesson, we discuss only the length increase. In those days, we had volume change, volume increase, and the what is the other one? Volume increase and the area increase. But we don't want to think about that now. Right? The strain is somewhat important topic than simply the extension. Right? To give the same extension, this must be this force must be 2F. Then only you get the same extension. I mean, same strain. The strain is important than the extension. E over L. To give the same strain, we have to take that strain. Okay. Just write under that strain is given. Change in measurement divided by the original measurement is known as the strain. Write that strain equals change in measurement divided by original measurement. Right. Important point is what? There is no dimension or unit for the strain. If you remember, under the measurement, you have learned the strain that saying that there is no dimension or unit. Today only you knew that what is the strain. Okay. By default, you know that there is no unit or the dimension for the strain. But today only you learn it properly. Strain is not have any dimension or unit. Right. Types of strains and the stress. Let's move to that. Look at here. You have a certain length. You have a certain length. You may apply certain force on it. The cross section of that is capital A. Capital A. So due to that, the length would increase. Length would increase. And the extension is E. Let's say the extension is E. The original length is L. Original length, we'll take it as L. Simple L. Okay. Right. So this is called the tensile stress. What is that? Sigma equal F over A. That is called the tensile stress. For elastic material, the length, if the length increase when you apply certain force on it, then the stress is called the tensile stress. We give a name for that. Tensile, like a tension development, tensile stress. It's called the tensile stress. Tensile stress. If you take the strain, we call it tensile strain. E divided by L. We call it tensile strain. Right? Let's say you have a rubber rod. You may have a rubber rod like this. The cross section is same as A. You apply certain force on it. When you apply certain force, what will happen? The length of that would decrease. Length would that decrease. This is simple E. The cross section is A. Cross section is A. The stress is equal F over A. This is called compressive stress. You like a compressive thing. It's called compressive stress. We call it compressive stress. Then the strain is called, these are just names, E over L. It is called compressive strain. Compressive strain. We call it compressive strain. These are names. When I have a tensile stress, you need to know that the length would decrease. When we say compressive strain, you know that what will happen to the length of it reduce. These are just names. Commonly for the tensile stress and the tensile stress and the tensile or the compressive stress or the tensile strain and compressive strain, we call it longitudinal. Compressive stress and tensile stress is called longitudinal stress commonly. Longitudinal stress. Tensile strain and compressive strain is commonly called longitudinal strain. They are just names, Lamaya. They are just names. Okay. Types of stress and strain. A rubber cord is stretched by two forces applied normal to its cross-section area. Elastic force unit area in this is called the tensile stress and the strain is called tensile strain. Right. Can you row this one? Okay, done, right? If the cylinder is compressed, under the action of applied force, the elastic force per unit area is known as compressive stress, and the strain is known as a compressive strain. Shall we draw that part? Right, done. Eh? Tensile stress and compressive stress can also be termed as longitudinal stress. In both above cases, there's a change in the length of the rod. The change in length to the original length of the cylinder is known as longitudinal strain. Okay, it's clear, I think. Now we will move to a very important part, the graphical representation of variation of load which is applied to the wire with the extension. Right, let's move to that part. It's another important part, I must say, under the elastic section, Let's say you have a like a copper wire, maybe copper wire, and it is connected with a certain scale fan, and you are placing certain mass on top of it. Based on the mass, there will be an extension, isn't it? Let's say the original length of that is this position, the original length is L. Based on the mass that you place, there is extension. Actually, this would provide the mg which is equal to x. You increase mg value like 0.5 kg, you are keep on increasing that value. If you do that, and what we are trying to do, we try to plot a graph how this force change with the extension E. Actually, that is the external force, how the external force change with the extension. Actually, that is external force means something similar to say elastic force. How this elastic force change with the extension. That's what we are trying to discuss here. Okay, how this force change with the extension. At the beginning, this is I will draw the graph and explain how it happened and what are the things that you need to know. These are few important points that everyone need to know. At the exam also they would ask you to draw that. C, D. These are special points. I will explain one by one. They would ask you to draw this graph, okay? At the exam also they would ask you to draw. So remember how you are going to do it and what are the important points under this graph. From O to A, you put some mass on top of it. Based on the mass, the extension is proportional. The force is proportional to the extension. Are you clear with that? The force is proportional to the extension. That means if you apply, I will go with the value. If I go with the values lamai, this is the force and that must be the extension. 0, extension is 0. 1 Newton, Newton. 1 Newton, extension would be 1 millimeter. 2 Newton, 2 millimeter. 3 Newton, 3 millimeter. 4 Newton, 4 millimeter, like that. Based on the force, extension is proportional. So this particular point is known as the proportional limit. Proportional. Proportional limit. Proportional limit. If you go beyond that, what will happen? These are properties of wire. Like if you take a copper wire, the brass wire, or the steel wire, these properties are still always there. Always there. If you apply 5 Newton, let's say 5 Newton is kind of mass, no, let's take an kind of values like 5 Newton. When you apply that, what we supposed to take for the extension, it is 5 millimeter, but unfortunately, it is not 5 millimeter, it is 5.5 millimeter. 5.5 millimeter. What you have learned, what you have observed, extension is something more than what we expected. Something more than what we expected. Actually, for a material like this, for the copper wire or the brass wire or the steel wire, there are several properties, right? One is called elastic property, other one is called plastic property. Elastic property, another one is called the plastic property. I will tell you what is meant by that. Right. Here, this one, actually first I will explain that elastic property means if you have that means you keep on applying a certain force. Once the force is released, it will come to the original length, original shape, right? Plasticity means something different. If you give a kind of deformation, it is permanently established there. The quality of being easily shaped or molded. That's what we call the extension. Sorry, that's what we call the plasticity. If you take metal rod, if you bend it like this, isn't it keep in the same shape? It will definitely keep the same shape. If you bend it like this, can keep the same shape. That is what we call plasticity. For a material like copper, aluminum, those things, there are two properties. One is the elasticity, another one is the plasticity. Actually, from here to there, elasticity is there. Once you release the force, it will definitely come to this point. And also, up to this point, only what we have is the elastic property of that material. Elastic property of that material. Beyond that, capital B is called elastic property. Right? Elastic, capital B is called elastic point. Elastic point. Elastic point. Capital B is called elastic point. From point O to B, what you have only elastic properties. After point B, elastic property and the plastic property combination exists in this material. What do you mean by that? After point B, if you release, if you release, it never come along this mark. Instead of that, it will give a permanent deformation. It will give a permanent deformation, permanent extension, permanent extension, like this. It will never come along this line. Instead of that, it comes to this position. Permanent extension is there. ඔයාලගේ මේව ඔයා day to day apply කරනවා මේව observe කරනවා මෙන්න මෙතෙන්ට වෙනකම්ම දැන් මෙන්න මේ location එකට වෙනකම්ම ඔයා 5 unit remove කරොතින් මේකේ තියෙන mass එක remove කරොතින් extension එක කීයද? final extension එක 0. මේක remove කරපුවොත් 5 newton remove කරොතින් extension එක 0මයි වෙන්නේ. ඒක තමයි අපි කිව්වේ point B වෙනකම්ම තියෙන්නේ elastic properties කියලා. elastic property විතරයි තියෙන්නේ. හරි. ඊට පස්සේ මෙතනින් පස්සේ plastic property plus elastic property combination එකක් තියෙන්නේ. එතනදී වෙන්නේ material එකේ permanent deformation එකක් තියෙනවා ඒ plastic property නිසා. මෙතනින් එහාට for example somebody apply 10 newton 10 newton help කරනවා මේ B කියන point එක find. ඒතර force එක වැඩි වෙනවා. හැබැයි ප්‍රශ්නේ තියෙන්නේ එයා මේ track එකේ එන්නේ නැහැ එතනදී. එයා එන්නේ වෙන track එකක. වෙන track එකක තමයි එයා එන්නේ. මම කියන එක පැහැදිලිද? ඔයා මේ rubber band එක මෙහෙම apply කරලා force එකක් when you release that it will come to the original length. If I increase it further increase, now what will happen and release when I release it now the length of this rubber band is more than the original length, isn't it? Don't you feel that? ඔයාගේ shocks එකක් ඔයාගේ මේස් දෙකක් ඔයා ආරම්භයේදී දානකොට ටිකක් අමාරුයි දාන්න. හැබැයි ටික දවසක් දානකොට මේස් එක නිකන් ලේසියෙන් දාන්න පුළුවන්. ඒකේ permanent extension එකක් තියෙනවා. නේද? සරලවම දාගත්ත හැටි. ඒ කියන්නේ permanent deformation එකක් වෙලා තියෙන material එකේ. initially තමයි අමාරු. හැබැයි time එකත් එක්ක deformation එක දෙනවා. ආයේ එකම විදිහක නෙමෙයි ඔය force එක apply කරලා ඔය කකුලට දාගන්න ඕක. ඒකේ විවිධ time වලදී විවිධ force එක apply වෙනවා. එතකොට මේ permanent extension එකක් තියෙනවා. සමාජවාදී ටික කාලයක් කරලා ඔය මේස් එක අයින් කරන්න වෙනවා. Yes, the rubber band also that happened. I mean, not the same shape, right? මේ shape එක නෙමෙයි rubber band එක නෙමෙයි වෙනස් එකක්. But rubber band also permanent deformation is exist. You apply certain large force. Right. Capital C is called yield point. Y-I-E-L-D. Yield point. We call it yield point. Capital C is called yield point. Yield point. Capital C is called the yield point. What is the important point under the yield point means? It is the point where after that point totally plastic property is available. I'll repeat it again. From O to B, you have only the elastic properties of this material. Elastic properties only there. B to C, the plasticity and the elasticity, both combinations there. I mean, several instances you get the several forces, several properties. After point C, only the plastic properties available, elastic properties not there. So C is called the yield point. After C, what will happen? The small kind of vibration is there, and you can further increase the force that you apply. Right? You can further increase the force that you apply. When you apply a large force at a one instant, the necking, we call it necking, the diameter of this material would start to reduce. The diameter of that material, let's say this is the initial diameter of that. But when you apply this kind of instant, the necking would start. Capital D is the maximum. Capital D is the maximum applied force. Maximum applied force. We call it maximum applied force. Okay. After point B, we don't want further large force to break it. After few seconds, if you do the same process, after necking form, definitely at this point, it starts to break. Capital E is something less than the maximum applied force. It is capital E, we call it breaking point. breaking point. So you don't get this kind of idea anywhere else. So get the maximum. Get the maximum. Literally, I'm teaching you all. Even you can learn things literally. I will repeat the same graph with several examples because I know that when I do my A levels, I also feel some difficult points to remember this graph. So I'll give you kind of ideas here to remember. Okay. Maybe is there any student who can't understand Sinhala? Any student who can't understand Sinhala? None of you, right? Okay. Maybe ඉතින් මෙන්න මේ වගේ දෙයක්. මෙන්න මේ වගේ එකක් හිතන්න. You have a bridge, you have a metal rod, and there's a river under this. So the people are using this metal rod to travel from one village to other village. Under this, you have river. Okay, there's a board saying that don't go more than 2 people at once. Right? Board එකක් ගහලා තියෙනවා මිනිස්සු දෙන්නෙක්ට වඩා මේකෙන් යන්න එපයි කියලා. එතකොට ඔයා එනවා ඔයාගේ weight එක let's say 50 kg. එතකොට 50 kg වගේ කෙනෙක් ඇවිල්ලා මේකෙන් මෙතනින් මේ පැත්තට යනවා ප්‍රශ්නයක් නැහැ. හරි. ඒ කියන්නේ මෙන්න මේ වගේ තැනක එයා එතනින් නැගලා එළියට ගියාම නැවත ආපහු ඔය කියන රොඩ් එක අර පරණ ලෙවල් එකටම එනවා. හරි. ඊට පස්සේ මං වගේ කෙනෙක් එනවා ටිකක් ඔයකට වඩා බර වැඩි. එතකොට මං වගේ කෙනෙක් ආවහමත් ප්‍රශ්නයක් නැහැ. මෙන්න මේ වගේ තැනකට ඇවිල්ලා එයා එතෙන්ට එනවා. හරි ප්‍රශ්නයක් නැහැ. These are examples. දැන් අපි දෙන්නෙක් නගිනවා මේකට බෝඩ් එකේ ගහලා තියෙන maximum allow for only for 2 people at once. No, me and another guy would come to this position, bridge, and travel from this point to that point. Here no problem. Up to this point it's applicable. It goes up to this. So finally what we could see, there is no permanent bending in this bridge. Still it is horizontal, right? So there is a stupid one came and with few colleagues, and he saw the board and saying that's like the maximum allowable is 2 people. So the stupid peoples are there. No, everywhere the stupid guys are there. So what he suggests from they are their friends. So let's go all together. Why we need to go only 2? So let's forget about board and go all together. Let's say 4 of them. 4 of them now get into this bridge and start to travel. What will happen? They could able to travel from this position to that position, no problem. But only thing is, after they travel, there's a permanent deformation. Now this bridge is like this. It is somewhere here. It is somewhere here. Can you understand that? Yes or no? So what will happen? The guys are now jumped to the other village, but problem here is the bridge is not exactly horizontal. It's like a bit. Did you get my point? How these things are developed up to that level? Okay. So now what will happen? There is like 20 people. 20 people. More මිනිස්සු 20ක් විතර වගේ එනවා මේකේ. ඔය බෝඩ් එක ගැන හිතන්නේ නැහැ. 20ම නගිනවා එකපාර මේකට. නැගලා යන්න යනවා මෙතෙන්ට. නැගලා යනකොට අමාරුවෙන් මේ වැඩේ කරගන්න පුළුවන්. එහා පැත්තේ විලේජ් එකට කොහොම හරි යාන්තම් පැනගත්තා. ඒ මිනිස්සු ලකි ඒ මිනිස්සුන්ට පැන ගන්න පුළුවන් වුණා. ඊට පස්සේ ඔය ඕක නිසා ඔය මිනිස්සු 20 ඕකේ ගිය නිසා මෙන්න මේකේ ස්ටාර්ට් කරනවා පොඩි නෙකින් එකක්. Necking means the diameter of thickness of this metal structure now reduced to a certain level. certain level. Did you get my point? Because of this stupid 20 people, another four people reach to this location from there to there. What will happen even after four people travel from the up to this level start to break? That is what the breaking happened. Did you get my example? Right? How about the other students? Did you get it properly? ඔය ටික මතක තියාගන්න බලන්න. ඔයාලට කවදාත් ඔක අමතක වෙන්නේ නැහැ. දැන් මට අපිට ඕවා මතක තිබුණ නැහැ ඇත්තටම. නමුත් අපි ඔයාලට මේක ටීච් කරන්න නිසා අපි මෙතඩ් එකක් හදා ගන්නවා. ඉතින් මේ වගේ මතක තියාගන්න try කරන්න. ඒ වුණොත් ඔයාලට මේක අමතක වෙන්නේ නැහැ. නැත්නම් ඔක ටිකක් අමාරුයි section එක අමාරුයි. මතක හිටින්නේ නැහැ. At the exam they would ask you to draw this graph. Simply for a ductile material, we call it ductile material means like the spring, sorry, the metal rod, metal wire, steel wire, copper wire, like that. They are called ductile material. For ductile material, this is the usual graph. There are two things: ductile material and what is the other one? What is the other one? Brittle material. Brittle is something different. I will explain that later. Okay, can we come to the graph? I think if you can understand the graph, that's you get certain knowledge. ඒක ඔය example මේ exam එකට ළඟ තියලා කියලා ඕවා කියන්න වෙලා නැහැ. ඒකයි කියන්නේ අර reverse class එකක තියෙන වැදගත්කම. example ගන්න ගියාම ඔළුවට එනවා තව කොච්චර කරන්න තියෙනවද කියලා. මේ වගේ ප්‍රශ්න ටිකක් එනවා. ඒක නිසා මම කියන්නේ ඔයාලට ලැබෙන benefit එකෙන් ප්‍රයෝජන ගන්න. reverse class එකට regularly join වෙන්න live class එකට. ඒතර ඔයාලට මේක leisurely ගන්න පුළුවන්. අමුතු දෙයක් නෑනේ. Now the time is 9:20. I think I could complete this lesson before 12:30. 12:30 නෝක අපි මේක ඉවර කරනවා. එතකොට තනි lesson එකක් පාඩ පුළුවන් වෙනවා. Right, graphical representation of variation of the load. It is not load which is applied to the wire with the extension. Consider a wire made out of materials such as iron, steel, copper, or brass. If such a wire is suspended in a vertical position, the forces are added to the lower end. We can observe increase in length for low values of the applied force. The force versus the extension graph will be a straight line. Okay, if we increase the force further after a certain stage, the extension is more than the expected value. A graph becomes a curve, a graph from A to B. The force is not proportional to extension. Now I want you to draw this graph. This is called the permanent extension or the permanent set. Draw this graph and mark this location in the space provided. Point A is a proportional limit. Point A is a proportional limit. Point A is a proportional limit. Okay, I think completed. Ne? Right. Even in this section, up to a certain value of the force, when the force is totally removed, the wire will come back to the starting length. Further increase in the force will continue an extension more than the expected, but when the force is removed, it will never come back to the original length. The material is said to have permanent set extension. Further increase in the force, the large amount will make the wire extending irregularly. Then at one stage, a neck will be formed and break after that. Okay. Right. Let's move to that. From we will write like this. The space is not provided for that. But anyway, in the last page, if you have the space, no problem. You can use that. A small subtopic you can use after the page number. After the page number 10, the space is provided. 2 pages were given for you to write anything. එතන අපිට පුළුවන් ඕන ලියන්න 11 number page number 11 වල ලියන්න පුළුවන් මෙන්න මේ content එක elasticity right subtopic you have learned that we have given the idea, but when you write that part together, elasticity, the ability of object or material, ability of object or material, ability of object or material to return its normal shape its normal shape after being stretched or compressed, after being stretched or compressed, after being stretched or compressed. After being stretched or compressed. Next point, plasticity. 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 The quality of being easily shaped or molded. Quality of being easily shaped or molded. Right. Now come to the location where we stop. You can write from O to B, right, like this O, B, only elastic behavior, only elastic behavior, only elastic behavior, only elastic behavior. B to C, elastic behavior plus plastic behavior, elastic plus plastic behavior. Beyond C, beyond C, plastic behavior, plastic behavior. Okay, look at here. Look at here. If you consider the stress equal force multiplied by area, force multiplied by area. So that means force is equal to area into stress. Force is equal to area into stress. That means force is proportional to stress given that the area is constant. Given that the area is constant. Okay. Similarly, strain equal E over L, E equal L into epsilon. That means L is original length, it is a constant. So extension is proportional to extension, strain. If somebody draw the stress versus strain graph, stress versus strain graph, strain, he would obtain the same graph, isn't it? Stress means force divided by area, strain means E divided by L. Same graph could obtain, isn't it? The reason is I explained force equal stress equal proportional. Extension equal strain equal proportional. Okay. Yes, the same graph could obtain. The same graph combined. A graph combined. Variation of stress with the strain for a wire. As the cross-section area and the initial length of the wire is constant, the stress is only depends on the applied force and the strain is only depends on the extension. Stress versus strain graph for a wire is same as the force versus extension graph which we draw above. Can you draw this one again? But remember to mark the stress, the strain there. මේ නම් මෙහෙමම තියෙනවා A proportionally with B elastic point, C yield point, maximum applied එතන විතරක් වෙනස් වෙනවා maximum applied stress. It need to be maximum applied stress. D point එක වෙනස් වෙනවා දරුවා maximum applied stress. E breaking point. Breaking point. Okay, done. Right. Right. Okay. For a brittle matter, there is something called the brittle material. The brittle material means like chalk. If you take a chalk, if you twist it, can you do that? If you try to bend it, what will happen? It break into pieces. If you take chalk, the magnet, or the concrete, those are supposed to be in porcelain. Those things are supposed to be glass, the brittle material. Those are supposed to be brittle material. Brittle material means if you analyze the graph of that extension, the stress versus the strain graph, it is something that we could obtain. Only the elastic properties maintaining, no plastic property. If you have plastic property, when you break it, when you bend it, it has to be maintained the same shape. But that won't happen for the chalk, concrete. You don't have that idea. Chalk whiteboard sorry, blackboard chalk make a bend thing or a bend a brittle material. Call it brittle material. Only the proportional limit, only the plastic behaviors, only the elastic behavior is there, no plasticity. These B is maintaining, A is the proportional limit, B you can say breaking point. Breaking point. B one pass a break pedal. Okay. Right. Then we have vehicle වල අහලා ඇති දුනු කියලා එකක් තියෙනවා දන්නවද? ලොකු ටිකක් ලොකු වාහනවල බස් වල lorry වල they are not using like normal suspension, they have some kind of spring system. දුන්නක් කියලා කියන්නේ. ඕවා තමයි ගන්නේ සාමාන්‍යයෙන් පිහි වගේව හදන්න. පිහි කඩු ඒ වගේව හදන්න ගන්න ඒවා තමයි. Right? Actual scenario is though that material is a brittle material. It's difficult to bend. Difficult to bend. That is why we use those things as well as suspensions for vehicles. Right? They are brittle material. In a vehicle, if it's like drop into a small dip, if you take a small dip, if it give a kind of deformation, permanent deformation, there's a big issue. දුන්න ඇදලා තිබ්බොත් මොකද වෙන්නේ? එහෙම වෙනවා. දුන්න ඇදලා තිබ්බොත් issue එකක්. So what we do here, we to prepare, let's say we need to prepare a knife or a sword. ඔයා ඒක කරන්න ඕන නම් ඔයාලා දැකලා තියෙන අර කම්මල් වල මිනිස්සු use කරනවා, like they take a small piece of that section and they do some modification. They heat up using a kind of device and again press it to get the same shape. Don't you know that? Right? They press it, they use hammer to press it and do some modification. They take a certain shape on that knife. Until the shape is take, they do that modification. Heat karnawa, karanawa, heat karnawa, karanawa. Right? So once you do that like when you heat up and do this pressurizing part, after that you keep that like a it keep to cool in normal air. We call it air quenching. These are not needed for you, but you get to get an idea about that. I'm trying to tell you how this knife or sword is prepared, like a solid material, hard material, strong brittle material. ඔක ගත්ත ගමන් මේක strong නෑ. දැන් strong නැතුනොත් මොකද වෙන්නේ? අපි හිතමු අපි කඩු ෆයිට් එකකට යනවා. නෑ හරිද? අපි කඩු ෆයිට් එකට යනවා. කඩු ෆයිට් එකට ගියාම අපි කඩු වන්නකොට දෙපාරක් වදිනකොට කඩුව කැඩෙනවා. ඒක මේ බ්‍රේකින් ස්ට්‍රෙන්ත් එක බ්‍රේකින් පොයින්ට් එක ගොඩක් ළඟ නා. දෙපාරම කරනකොට කඩුව කැඩෙනවා. ඕක වෙන්න හොන්නේ නෑනේ. ඕක වෙන්න නෙමෙයි අපි මේක කරන්නේ. එතකොට ඒක ස්ට්‍රෝං කරන්න ඕන. ස්ට්‍රෝං කරන්නේ කොහොමද කියලා මේ කියන්නේ. දැන් ඔයාගේ නයිෆ් එකක් ගත්තොත් නයිෆ් එක ළමයි මොකක් හරි එකක් අම්මා හරි තාත්තා හරි අපි හිතමු මොකක් හරි එකක් කපනවා කියලා නයිෆ් එක ගන්න. ඒකනේ. එතකොට ඕක කරනකොට ඕක ස්ට්‍රෝං නවුනොත් ඒකට අගල කඩල යනවා. බ්‍රිටල් නේ. මැටීරියල් එක බ්‍රිටල්. ඒකද කරලා යනවා. ඒකට අපි ඒක නවත්තන්න ඕන. සහ ඕකේ ඉලාස්ටික් ප්‍රොපර්ටි ඕකේ මේ ප්ලාස්ටිසිටි තිබ්බොත් මොකද වෙන්නේ? ප්ලාස්ටිසිටි තිබ්බොත් මොකද වෙන්නේ? Plasticity තිබ්බොත් එහෙම material එක when I using the material and if I want to cut something, what will happen if I give a small bend? What will happen if I give a small bend? Bend එකක් තිබ්බොත් මොකද වෙන්නේ? Knife එක වාගේ ටික වෙලාවකින් මෙහෙම තියෙන්නේ. If the plasticity is available, because it give a permanent deformation. If the plasticity is available, you can bend it like this. But knife, when you bend it, it comes to automatically the same shape. Because the plastic behavior need to be removed. If it's a good property, good material, that property should maintain. Understood? What I want to tell you, we need to make a strong brittle material for to develop good sword or strong sword or a knife. අපි ඒකට කරන්නේ අර මම ඉස්සෙල්ලා කිව්වේ කම්මලේ ඒක තමයි කරන්නේ. ඒක යා රත් කරනවා අපිට ඕන ෂේප් එකට ගන්නවා. එයා ඒකේ ඒක කූල් වෙන්න අරිනවා. අපි ඒකට කියනවා එයා කොන්චින් කියලා. එයා කොන්චින්. ඊට පස්සේ එයාගේ ෂේප් එකට ආවම එයා ටික රත් කරලා ඩක් ගාලා දානවා වතුර එකකට. වතුර එකකට දැම්මාම that becomes strong material. That is the best material now. Strong brittle material. That is how the sword is prepared. එක sword එක හොඳ එකක් නම් හොඳ material එකකින් හදපු එකක් නම් ඒක නැමුණාම නැමිච්ච එක නමපුවාම නැමුණ පාරවල් තියෙන්න බෑ. ඒක හොඳ එකක් නම්. ඔයාට චෙක් කරන්න පුළුවන් ඔයාගේ ගෙදර තියෙන knife එක නමලා බලන්න නමලා නැමුවාම නැමිලා තියෙනවා නම් ඒක material එක හොඳ එකක් නෙමෙයි. ඔයා මං හිතන්නේ ඔයාට මේක ඔයාගේ parents ට කියන්න බං knife එකක් හොඳ එකක් ගන්න කොහොමද? නමලා බලන්න නැමුවම ඒක bend එකේ පොඩි හරි ප්‍රමාණයක් තියෙනවා නම් that material is not good. Okay? And you know that these things you know clearly. So when you if you all are not doing exercise, right? You know that our tendons are there. No? Within the tendons, the materials are deposited. So then these material, these tendons are become brittle, more brittle, right? More brittle. Naturally, when you are getting older, definitely this material or the tendons become brittle. The bones are become brittle. That could happen. But if you are not doing exercise, the material are deposit these layers, these locations. Finally, what happens? These tendons become brittle. It's difficult to bend. So it is better to do regular exercise. The problem is the time, but anyway, it's better to do regular exercise. The most, I can say, the most healthiest person in this world is what do you think? What kind of the people who what kind of the people doing what kind of sports? Any one of you? Not the runners. Not the runners. Yes, exactly, Kavisha. Very good. It is gymnastics. Yeah, that is the point. Gymnastics. So they are very flexible. If you can keep your body like rhythm like a flexibility, even though your age is just a number, even though you get older, the age is just a number. Just remember, right? I'm not doing that, but I'm telling you to practice that. අර පුළුවන් නම් ආයේ ටෙන්ඩන්ස් ඔයා එක්සර්සයිස් කරලා තියාගන්න ජිම්නාස්ටික් කරන එක තමයි හොඳම එක්සර්සයිස් එකක් ඒක ලෝකයේ පිළිගන්න එකක් එතකොට ඔයාගේ පුළුවන් මේ ටෙන්ඩන්ස් අර බ්‍රිටල් වෙන්නේ නැතුව තියාගන්න ෆ්ලෙක්සිබිලිටි එක තියාගන්න ඒක ඔයා යන් වෙනවා you are looking young even the yoga I think that's best I don't know exactly the internal thing here but gymnastics is the best thing yoga is something similar to that because we are doing some kind of difficult exercise there. Exactly, I don't know about the yoga, but I think it's better. Right. there is some kind of person called Robin Fernando. Haven't you heard that name? Robin Fernando. Robin Fernando. Anyone knows about that name? Unfortunately, no. Robin Fernando කියලා කියන හොඳ ජිම්නාස්ටික් ප්ලේයර් කෙනෙක්. ඔයාගේ පේරන්ට්ස්ලා දන්නවා ඒක අහලා බලන්න. එයා හොඳ ජිම්නාස්ටික් ප්ලේයර් කෙනෙක්. එයා ජිම්නාස්ටික් ප්ලස් කරාටි දෙකම. එයා සාමාන්‍යයෙන් කියන්නේ විජේ කුමාරතුංගට වඩා අවුරුදු 10ක් විජේ කුමාරතුංග I think you know about විජේ කුමාරතුංග. විජේ කුමාරතුංගට අවුරුදු 10ක් වැඩිමල් කියලා තමයි කියන්නේ. හැබැයි ලුක් එක ගත්තාම ජිම්නාස්ටික් ප්ලේයර් කෙනෙක් අරයා හරියම අවුරුදු 80ක් 90ක් වෙනම එයාගේ වයස තිබ්බත් එයා young looking. එයා ජිම්නාස්ටික් නිසා තමයි කියලා තමයි කියන්නේ. හරි. දොරාත් ඉඳලා බලන්න ජිම්නාස්ටික් කරනවා නැද්ද කියලා හිතලා බලන්න. Okay. Right. Visheshan, if you have your grandfathers or grandmothers, don't let them drop down to the ground. Right? If they drop down to the ground, their structure is brittle now, so brittle now. Right? You can't develop their structure with the age. එයාලා brittle වෙලා තියෙන්නේ. ඒ කියන්නේ චෝක් එක වගේ ඩස්ට් එක වගේ කඩලා යනවා. චෝක් එකක් කරනවා වගේ තමයි ආච්චි කෙනෙක්ගේ සීයා කෙනෙක්ගේ ස්ට්‍රක්චර් එකක් කරනොත් එහෙම. ඒක හදන්න බෑ. අමාරුයි. young නම් ඒකේ අත්‍තරම මේ young නම් ඒක brittle ගතිය අඩුයි. because you young, you are doing something no. young නම් ඒක brittle ගතිය අඩුයි. ඒකට young විදිහට ඉන්න නම් ඔයා එක්සර්සයිස් කරලා ජීවත් වෙන්න ඕන. කාරණා දෙකක්ම තියෙන්නේ. එක්කෝ උඩා කල් ජීවත් වෙන්න හදන්න හොඳ නෑ. Right? Don't take this as serious thing, but if I believe that we don't want to live a very long life. Right? අපි ගොඩාක් කල් ජීවත් වෙන එකට වඩා ඉන්න කාලේ හොඳින් ජීවත් වෙන්න තමයි බලන්න ඕනේ. ගොඩාක් කල් ජීවත් වෙනවට කමක් නැහැ. අපි හොඳින් ඉන්නවා නම් ඒ කියන්නේ අපිට පුළුවන් අපේ වැඩ කරගෙන යන්න, ඒව ටික කරගෙන යන්න ඕකේ. එහෙම නැතිනම් ගොඩාක් ජීවත් වෙන්න ගියොත් අමාරුයි. අපිට අමාරුයි. අපි බලා ගන්න පුද්ගලයන්ට තමයි. ලයිෆ් එකේ අර වගේ දෙයක් කරනවා හොඳයි. කියන්නේ ඒකෙන් කියන්නේ නැහැ මේ වේලස්සන කොහරි යන්න ඕනේ කියලා එහෙම ගන්න මේ කියන්නේ. ඒවනේ මේ කියන්නේ දැන් සමහර කට්ටිය බලාපොරොත්තු වෙන අවුරුදු 100ක 110 ඒ රේන්ජ් එකට යන්න. ඒ වගේ රේන්ජ් එකට ගියාම කොම්ප්ලිකේට් වෙන ලයිෆ් එක. ඒ වගේ එකකට ඕනේ නැහැ. හැබැයි අපිට අපේ වැඩ කරගන්න පුළුවන් ලෙවල් එකකින් යහපැත්තේ අවශ්‍ය නැහැ කියන එක තමයි මම හිතන්නේ. right okay. මම ඔයාලට කිව්වාගේ ආච්චි සහ සීයා පරිසම් කරන්න වැටෙන්න දෙන්න එපා. වැටුනොත් අර යාලගේ ස්ට්‍රක්චර් එක brittle වෙලා තියෙන නිසා ඒ ස්ට්‍රක්චර් එක ළමයි holes තියෙනවා. when you get older there are some small holes inside this structure. skeleton එක ගත්තොත් there are some holes inside it. with the age that would happen. you can't avoid it. එතකොට ඒක brittle වෙච්ච ඒ brittle ගතියත් ඒකෙන් වැඩි වෙනවා. කරනවා තමයි අමාරුයි හදන්න ඊට පස්සේ. right, let's move to that brittle material. Some material breaks just after reaching the elastic limit. Elastic limit. This is the elastic limit, and even it's the breaking point. Elastic limit. These are known as the brittle material. Glass, concrete, chalk. Stress versus strain graph for those materials are as follows. Right? Can you draw that? Breaking point and elastic limit. So don't you feel that this is a very good subject for you all to learn? don't you have that interest? You should have that interest, Lamai. Otherwise, difficult. Right. Okay. Right. Let's move to Hooke's law of elasticity. Hooke's law, you have learned Hooke's law, but it is time for you to learn it properly. Hooke's law. Look at here, Hooke's law. What is meant by Hooke's law? If you take the graph that we plot, if you take a graph that we plot, Lamai, right, up to this point, O to A, which is known as the proportional limit, O to A, which is proportional limit, it is said that even if you draw that force versus extension graph, it is said that force is directly proportional to extension. Force is directly proportional to extension, right? Force is directly proportional to extension. Here, the force then equal K into E, right? K is called the spring constant or the force constant, where K is called spring constant, force constant. K is called spring constant or force constant. I think you know about this idea. Unit of K, it is Newton per meter. Newton per meter. Okay, right under that. Now, there's another part I will explain. First, we will complete that part. Hooke's law of elasticity. The force exerted on the wire which is under proportional limit, only for the proportional limit. Only for the proportional limit. Only for the proportional limit is directly proportional to the extension. Force proportional extension F equal KE. K is called the force constant. Most of the time we call the force constant. If it is a spring only, spring constant is maintained. So you better write force constant here. Unit of K is this Newton per meter. Right, look at here. If you take the graph extension, stress versus the strain, stress is directly proportional to the strain under proportional limit. Under proportional limit. So the Hooke's law again modified as this way: sigma equal y into epsilon. Y is called the Young's modulus. For a solid, y is called the Young's modulus. Y equals stress over strain. That means here you can say that this is another important relationship. This also important. Here F over A equal Y E over L. F over A equal Y E over L. Y is called the Young's modulus. Young's modulus. Young's modulus. We call Y as the Young's modulus. Okay. Right. Hooke's law can be expressed in terms of stress and strain. The stress is directly proportional to strain for elastic material under proportional limit. Stress proportional epsilon, stress equal y into epsilon. You can write this one also. Young's modulus, y is called Young's modulus. Right. Here we only concern about the Young's modulus. If you consider solid, definitely we need to think about the Young's modulus. But for liquid or gases also, there are kind of deformation available. When you apply certain force, the gas also kind of give a deformation. Even the liquid would give a deformation. So these are called bulk modulus. We all are not discussing that. There are actually, if you look at if you read the text and the notes under these topic in extra note, there are like 81 modulus. 81 modulus. But we only concern about the Young's modulus because we only concern about solid here. Rigidity, I have given the Young's modulus, rigidity modulus, bulk modulus. There are like that 81 modulus which are not interested here. No need to think about that. Young's modulus, the only point we need to do. We need to know. Okay. Right. Young's modulus, I will define the Young's modulus. Look at here. Stress equal Y into extension strain. The unit of Young's Young's modulus, Newton per meter squared. Newton per meter squared. The dimension of Young's modulus, it is like ml minus 1 t minus 2. ml minus 1 t minus 2. Okay. ml minus 1 t minus 1 t minus 2. So the if you want to define the Young's modulus, you can simply say that it is actually this is for the for the tensile stress, tensile material, or the simply the ductile material. You can say tensile stress or compressive stress divided by tensile strain over compressive strain under the proportional limit. That's simply Young's modulus. It's called Young's modulus. Understood? Tensile stress slash compressive stress divided by tensile strain slash compressive strain under the proportional limit. That's what we call the Young's modulus. Okay. Shall I write the note? Young's modulus. Young's modulus is the ratio. Young's modulus is the ratio. Young's modulus is the ratio of the tensile stress slash tensile strain, sorry, compressive stress. Young's modulus is the ratio of the tensile stress within bracket compressive stress or slash whatever the case, compressive stress acting on a substance to the acting on a substance to the tensile strain within bracket compressive strain under proportional limit. Right. Complete up to that. Right, done, finished. Okay. So we will move to a few questions. Let's move to question number 16. Question number 16. This tutorial. Right, done. Okay, look at here. We will move to the question. A body of mass 10 kg is suspended from a wire of length 4 meter. Radius is this. Calculate the stress. How to find the stress? You may apply 10 kg means 100 Newton. The stress is equal to force applied, or the stress is equal to elastic force divided by the area. The stress is equal F divided by A. F equal 100, area it is 5R squared. 100, 5, 22 over 7. We'll make it as 5. Radius is 1 root 5. But we need to take the square of that. 100 divided by 5 over 5. It is cancelled. It is Newton per meter. No, there must be the radius need to be like 10 to the power minus 6 to make it meters. 10 to the power minus 6. So the stress is equal 100 into 10 to the power 6 Newton per meter squared, which is 1 10 to the power 8 Newton per meter squared. That kind of stress is developed, isn't it? 10 to the power 8, no? Calculate the elongation produced. Elongation means the extension. Elongation means extension. F or the stress over stress equal Young's modulus into strain. So the strain equal then stress over Young's modulus. Stress is given. We found it 10 to the power 8. Young's modulus 2 10 to the power 11. 2 10 to the power 11 means we can say that 0.5 into 10 to the power minus 3. 10 to the power, no unit for that strain. The strain is again equal elongation, extension over original length. Extension is equal to then length 4 meter, 4 into strain, 0.5, 10 to the power minus 3, which is 20, that means 2, 10 to the power minus 3 meter. In terms of millimeters, 2 millimeters, isn't it? 2 millimeters. Correct? If you completed that, we will move to another question, question number 17. Question number 17. I hope everyone got this answer. Question number 17. Okay, done. Let's move to the question then. A wire of length 2 meter and cross section and area 1 millimeter square supports a mass of 10 kg. Calculate the Young's modulus of the wire if the elongation produced it is 0.25. You have a wire length 2 meter. Cross section area is 1 millimeter square. The support a mass of 10 kg. 100 Newton. If the elongation produced in it is 0.25 centimeter, find the Young's modulus next. F over A, Y E over L. There are only three equations, F equal KE. Other one is F sigma equal Y into epsilon. Other one is F over A equal Y E over L. That's all three. F 100 cross section 1 millimeter minus 6 to convert into meters, cube square meters. Young's modulus extension 0.25 10 to the power minus 2, or the original length is 2. Y equal 100 into 2 divided by 10 to the power minus 6, 0.25 into 10 to the power minus 2. Y equal 100 into 2. I will make like 25 and 10 to the power minus 8, that means minus 10. Make a 25 karna, 10 to the power minus 4 karla. So 10 to the power minus 4 into minus 6, 10 to the power minus 10. What is that then? This is 4. 4 into 2, 8. 8, 10 to the power 10 Newton per meter square. Don't forget to put the units. 8, 10 to the power 10. Let's move to another question. Question number 18. Question number 18. How about the other students completed? Right, done, finished. Okay, next. Right, good. Let's move to the question. A wire of length 1 meter is stretched by a force of 10 Newton. The length of that is 1 meter. The cross section area also given 2 10 to the power minus 6. Young's modulus 2 10 to the power 11 Newton per meter square. Calculate the stress. The stress equal F over A, applied force 10 Newton divided by area minus 6, which is 5 10 to the power 6 Newton per meter square. The strain equal, to find the strain, we can use this equation. Strain equal 5 10 to the power 6 divided by the Young's modulus 2.5 10 to the power minus 5. That's the strain. Then the increase in the length of the wire, the strain equal E over L, E equal 2.5 10 to the power minus 5, 1 meter, that means 2.5 10 to the power minus 5 meter. If you go with the millimeters, it is minus 2 millimeter. The answer 18. Okay, right. Now we will come to again our note. The relation between the Young's modulus and the force constant. Look at here. The relation between the Young's modulus and the force constant. Let's say you may have a certain length. You apply certain force on it, F. The length of that is L. Because of that force, the length of that would increase by E amount. simple E amount. The cross section area of that wire or the whatever the case is A. Here, based on what we learned, F over A equal Young's modulus E over L. F equal A Y divided by L into E. And also based on what we learned, F must be equal to force constant to extension. Therefore, based on those two equations, it is very clear for a system like that, K must be equal to AY divided by L. Because for the given system, cross section is constant, initial length is constant, Y is constant. So it is AY over L. K equal AY over L. So the force constant depends on few factors. What are the factors? The cross section area of the wire. Force constant කියන එක depend on factors තුනක් මත එකක් cross section අනිත් එක Young's modulus අනිත් එක original length. ඔයාලට මතක ඇති අපි මේක we have discussed the force constant under the mechanics section but we don't know how it related. Now it is clear it is related to the cross section of the part, Young's modulus of the material and the length of the wire. Okay, right, shall we move to that part? Relation between Young's modulus and the force constant. Let's consider a wire which is having a cross section area A, the length L. Due to an external force, the extension of the wire is simple E. Right. Can you complete up to that point? K depends on cross section, initial length, and Young's modulus. Okay, done. Have you highlighted that K depends on cross section, original length, Young's modulus? Kavisha, the second one is the initial length. Initial length of the wire. Initial length. It is the initial length. Okay. Right. Based on the equation also you can understand A cross section, L initial length, I Young's modulus. Right. Okay. So I think it's better to have a small break. We will take a small break. We'll start it at like 7:30, but the students are not joining the 7:30, so I thought of starting like 7:40. Now the time is almost 10:30. We'll take a small break. Let's say we'll meet again on 10. Now the time is 10:30. We'll meet again on 20 minutes time, 10:50. Right? Take a small break. We'll conduct till 12:30 to complete this lesson. I think we can complete it today. We'll take a small break and join the class. Okay. Okay, shall we start? Right. Okay. Let's move to the section. Right. We will move to the elastic potential energy, which is known as the strain energy. That part. Right. What is the strain energy? If you take a rubber strips, if you take a rubber strip like this, right? Rubber strip like this, and if you release the rubber strip, you know that you can do some work because of this. Okay? If you take a rubber strip like this, rubber strip, right? Rubber strip like this, and release it with a small stone, you can do some work. That means you are doing some work to give extension. No? You are doing some work to provide certain extension. When it comes to original length, that energy is released. That energy is released. So that is how the strain energy is developed. You need to do work. That work need to be deposited on the system. That is what we call the elastic potential energy or the strain energy. Right? Simply, if you give a deformation to a certain substance, the energy is deposited on it. Energy is deposited on it. To give a deformation, the energy is deposited on it. Okay. Look at here. Let's say you may have a certain length. The certain length of this wire is L. You are applying certain force at point, let's say point P. The applied force, and because of this force, there's extension of E. The new extension is E. Right? You are doing some work to provide this extension. That energy is deposited on this wire or whatever the object. The work done is equal. The work done is equal force multiplied by displacement. That is equal to the work done. The only thing is here, the force that you apply at the original situation is how much? What's the value of that force? Force that you apply here at this moment? 0, not F. You just, there is no extension, 0 value. But when you have a higher extension, you can understand that now it is in the original length, no extension. You apply more force, increase the force. Now it is somewhere here. By increasing that force, you give extension. When it comes to this point only, the force applied is F. At the beginning, the force is 0. Understood? Clear there? Right? So that means the work done you can't calculate simply F into D, F into E. We need to take the average force in that situation. 0 and plus F must be divided by 2 to get the answer. The work done need to be modified. The work done equal the average force multiplied by displacement. Average force F plus 0 divided by 2 into E. Work done. it is equal Fe divided by 2. Fe divided by 2. That's the one equation. W equal, F you can replace F over A equal YE over L. Ne? F equal YE over L into A into E. W equal YA over L E squared. E squared. YA over L again equal to spring constant or the force constant. So this equation now become divided by 2 divided by 2. This equation become half K A K E squared. Half K E squared. With the spring constant or the force constant, you can develop this relationship. Or else you can use this one. Either one, but only thing is to get the knowledge. How we are going to do is using these equations. I use the average force. Reason is at this point no force applied, zero. Original length, they are in original length, okay, no force applied. But to give the more extension, the more force would apply. At this point only you get the F. We need to find the average force then. Right, done. Eh? Right, let's move to that. Energy stored in a stretch string. Let's consider a wire of length L and cross-section area capital A. The wire is subjected to two forces F1 and F2. F1 and F2, the two forces F1 and F2. I will take F. I will take the wire is subjected to force F. Better write like that. F under proportional limit. Under proportional limit. Under proportional limit. Strain energy by applying the force. If we increase the length of the wire of a cord, then the work done will get stored in the system as a straight energy. Straight energy stored in the stretch string. Let us consider wire of length L, cross section area capital A. The wire is subject to the force F, which is under proportional limit. The extension due to F is simple E. Right. Need to draw this figure. Okay, done. Average force from A to B. Average force from A to B. F plus 0 divided. Actually, it is A and B. Please take that as A and B according to the note I have given. A and B. This is A and this must be B. Average force from A to B. F plus 0 divided by 2. Extension due to average force. It is simple E. Then the work done equal average force multiplied by the displacement, and you can develop up to this equation. Up to that equation you can develop. Better complete that one also. The work done equal average force into displacement, and you complete up to that level. This is something important. This is also important, right? Now, what you are trying to do, you can plot a graph, force versus extension. Force versus extension. Everything we discuss here is the under the proportional limit. Okay, under the proportional limit. This kind of graph you could obtain for the proportional limit now, right? Not L squared, E squared, ne? Not L. It is E. Simple E. Make L name E. L method. Looks like E and L both are the same. It is L square, not L square, E square. Because we need to replace the force with this equation. When you have do that, you get extension at this point and that point. So you get E square. Right. Okay. Now look at here. We draw the graph completed for the force versus extension, and let us consider this area. This area equal, this is the extension E, and that must be the force half Fe. Half Fe, the work done. Half Fe is the work done. Area equal the strain energy. The strain energy. So that tells me the energy which deposited on a material due to deformation is given by area under force versus extension graph. Remember? Okay? Force versus extension graph. Right. Can you come to the note? Let's draw a force versus extension graph for the wire. Complete this. We have another part, but we don't want to draw it. Graph because we are interested about only the only for the elastic limit. Sorry, proportional limit. Okay, proportional limit. Right. This shows that the area under force versus extension graph represents the work done by the average force, and it is same as the strain energy. Please underline that the work done by the force, and it is the same as the strain energy. It is same as the strain energy. Let me to show you another important relationship. Let's say you have something like that. This is the area capital A. You may apply certain force on it. So when you apply certain force on it, this is the extension E. That is capital A. Right? The length of that is L. This also original length is L. Original length is L. Here, the cross section is A. The work done per unit volume, the work done is equal half Fe. Half Fe. I need to find the work done per unit volume. The work done per unit volume. If you want to find the work done per unit volume, the total work need to be divided by the volume of this system or the object, isn't it? Neither the volume of that. half FP need to be divided by the volume of it. Volume. Half F divided by volume tells you cross section into the length. We don't want to think about the extension, even though I draw in exaggerate way, the extension is very small. It is equal to half A over L divided by E. A over L. A into L is the volume. The work done for unit volume, let's say W double dash, which is W divided by volume. Work done divided by the volume. Work done divided by volume. W double dash equal half F over A E over L. What is this and what is that? It is the stress and that is the strain. W dash equal this equation. The work done per unit volume of this object or this system is equal to the half into stress into strain. Right? Remember that. If a graph completed for the stress versus strain, it is something like that, and there's another part we don't want to think about that. Under the proportional limit, think about the area of it. The area is equal then, area equal half sigma epsilon. What is that? The area equal, what is that? Half sigma epsilon means what? The area equal the work done per unit volume. The work done per unit volume. Work done per unit volume. Okay. The work done per unit volume. Right. We need to complete that. Write the subtopic. The work done per unit volume. Under the space provided, you can use this space. You can use this space to write this. The work done per unit volume. The work done per unit volume. The work done per unit volume equal the work done per unit volume equal work done divided by volume. Work done divided by volume. Now you can start with this point and complete up to this. Okay. If the space is provided, you can write under this. This shows that area under this shows that area under force versus area under stress versus stress versus strain graph, stress versus strain graph stress versus strain graph, represent the work done, the work done, the work done per unit volume, the work done per unit volume, work done per unit volume. Okay, right. I think you have certain idea up to now. No problem with that. Let us move to another small section. If you take a rod like this, the length of the rod is L. The length of the rod is L. Okay, the length of the rod is L. If you increase the temperature by delta theta, now you know that there's a length increase. L is original length, and there must be delta L amount. This length increase is equal delta L, let's say L alpha delta theta. Do you remember that? Under the thermal physics, we learned that. What happened if you do something like that? You may have the same rod. Only thing is, it is connected to the two ends, two rigid points, where it is not allowed to expand. Where it is not allowed to expand. So when it is not allowed to expand, what will happen? The compressive forces are developed, isn't it? The compressive forces are developed. The compressive forces are developed here. From this rod, from this surface, there is a force on the rod. From this surface, there is a force on the rod. And also, if you take the temperature reduce, let's say the rod is placed on the two rigid supports. If the temperature reduce, what will happen? If the temperature reduce, that total length need to be small, need to be decreased, but that won't allow. We don't allow it to expand. We don't allow to expand as well as the contract. So what happened? There's extension. There's extension, isn't it? There's extension. So the stress would develop on this. The stress would develop on these surfaces, this surface and that surface. So based on that, the thermal stress, we call it thermal stress. Because of the temperature difference, the thermal stress would develop. Understood? So here, if you consider this instant, when there's a temperature drop, there must be a kind of extension now. Because of that, අතර වෙන්න ඕනේ මෙයා මෙතෙන්ට අඩු වෙන්න ඕනේ. ඒතර මෙයා සහ මෙයා extension එකක් වෙනවා. What will happen? We can apply our equation F over A equal Y E over L. This is the thermal force actually. Because of the the temperature changes, this force would develop. F over A is called the thermal stress. It's called the thermal stress. Thermal stress. F equal A Y over L into E. E here is delta L. Extension, which is delta L. Correct? Delta L equal what? AY over L. Delta L equal L alpha delta theta. L alpha delta theta. L cancel. Here F must be equal to AY alpha delta theta. AY alpha delta theta. Okay. F equal AY alpha delta theta. So remember, if you increase the temperature while keeping this rod, while keeping the support at the two ends, where it is not allowed to expand or contract, thermal stresses are developed. Thermal stresses are developed. That values are given by this equation. F equal A is the cross section, Y is the Young's modulus, alpha is the, what is alpha? Coefficient of linear expansivity, delta theta. With this, you can find what is the force which develop. Can you complete this? Right, look at here. The stress introduced by a body which is constrained against expansion or contraction due to temperature changes. Consider a rod, a wire which is clamped at the two ends. Right, look at here, I will draw it. Please draw this figure. For this rod, alpha, capital A, the cross section, the length is L, Young's modulus is Y. What is alpha? Coefficient of linear expansivity. Coefficient of linear expansivity. Let us consider a situation where the temperature of the rod is dropped by delta theta amount. So the decrease in length which has to be for the rod delta L equal what? Delta L equal L alpha delta theta. L alpha delta theta. Can you complete up to this? Given like this, where the F is the force generated due to the contraction of the rod. Contract when contraction develop force. The above equation is true for temperature increase, rise. We did it for the temperature decrease, but remember it is still applicable, still correct for the temperature rise. Done. Let's move to question number 19. Let's move to question number 19. Try yourself. Question number 19. A steel wire cross-section area 0.5 millimeter squared is held between two fixed supports. .5 millimeter squared. If the tension in the wire is negligible and it is just stored at 20 Celsius, determine the tension when the temperature falls to 0. That means delta theta is what? Now 20 Celsius. Initially it was C20, now it is 0. That means contraction need to be there, but it can't because of this clamp. You can't contract. Determine the tension when the temperature falls to 0. Young's modulus is given 2.1 10 to the power 11 Newton per meter squared. Alpha 12 10 to the power minus 6 per Celsius. It is very simple. You can find the tension along the string. The tension along the string. How to find the tension along the string T? Let's say F equal AY alpha delta theta. That equation straight you can apply without any problem. You can apply this. Here F tension cross section 0.5. Put these values properly. Minus 6 Young's modulus 2.1 10 to the power 11 alpha 12 10 to the power minus 6 delta theta 20. So the tension now equal to, is this answer there? Did you get, anyone got this answer? I got it now. 25.2 Newton. The few students got these answers. Please check the rest of the students whether you got it. 25.2. Right. For this case, we have a very small practical. Only one practical we have under the elasticity, but if you look at the past paper, several times the same question asked. So we will move to this practical now, right? Page number 9. You can turn to page number 9. Measurement of Young's modulus available in the form of wire. In the form of wire, right? Right. So this method helps you to find the Young's modulus in the form of a wire. Normally, you need to take 3 meter length wire. Normally, 3 meter length wire you can take. The cross section is now something like 0.5 millimeter. I mean, diameter is 0.5 millimeter. It's a very thin wire, not the thick one, the thin wire. Look at here how we are going to do it. There must be identical wires, two wires. Identical two wires must be there. Two identical wires. This is the one. This is the one. The other one is this. They are identical wires. Only thing is, you may connect that into a main scale. You may connect that into a main scale. And the other wire is connected to a vernier scale. Other one is connected to a vernier scale. This is the main scale. This is the vernier scale. Let's say this y is Q, this y is P. Y is P and that is Q. You need to hang a dead weight, initial weight, we call it dead weight, capital M, it's a dead weight, to make it vertical only. To make it vertical, you keep that a dead weight, right? For the vernier section, time to time, we use certain math. I mean, the hanging weight is changing. Let's say this is simple length. You change simple length time to time. The increment is 0.5 kg. Increment is 0.5 kg. Right? The increment is 0.5 kg. Okay, the increment is 0.5 kg. So what we are trying to do here, we try to find the extension based on the mass that you have, the mass you use here. We try to find the extension very clearly and correctly using the vernier scale. Otherwise, we can't get the exact answer. We try to get it very accurate answer. That's the reason behind that. So there must be small thing to understand. I will share my screen to explain this. These are the two wires which I highlighted, P and Q. This is the dead weight, and you use different masses. Only thing is you increase 0.5 kg every time. You increase 0.5 kg every time. It is 0.5 kg always, right? Here, starting mass is 0. At the beginning, you don't have any mass on the wire Q, but now, sorry, it is 0. So the scale reading, when we added, you may have a certain value, 0 actually. When you add 0, when you have 0, no extension, isn't it? When adding a weight means 0 value, right? So when you add 0.5 kg, 0.5 kg, definitely this Q string would give a kind of extension. You can measure it from there. You can measure it from there. I'm repeating again. දැන් කිසිම weight එකක් නැති වෙලාවක මෙයාගේ reading එකක් තියෙනවා අපි ඒක ගන්න ඕන ඇත්තටම කිසිම value එකක් නැති වෙලාවක මෙන්න මෙතනදී කිසිම hanging weight එකක් නැති වෙලාවක reading එකක් තියෙයි you want to take that. Now you increase by 0.5 kg, you may have a new reading. Take that. You take another reading, new reading. Another 1.5 kg now, new reading. Like that, you take the reading. Now, how to find the extension? Of course, when you don't add any mass, you don't have any extension. It is definitely 0. But when you increase by 0.5 kg, the second reading is this is the first reading. The difference of that would tell you the reading for that. Understood? Clear? Not clear. දැන් මෙතනදී මේකයි කියන්න හැදුවේ. දැන් මේ ඉන්ස්ටන්ට් එක තේරෙන්න ඕන. ඒ කියන්නේ මෙයාගේ කිසිම weight එකක් නැති වෙලාවට මම මේ කියන්නේ Q ගේ. If there is no weight, no hanging weight, you may have a reading. You may have a reading. ඒ කියන්නේ vernier එකේ තියෙන position එකයි main scale එකේ තියෙන position එකයි එක්ක reading එකක් තියෙන්නේ මොකක් හරි. ඊට පස්සේ ඔයා මේකට 0.5 kg add කරනවා. You are going to increase 0.5 kg every time. 0.5 kg add කරපුවාම you may have a certain reading now because of the extension. Right? Again, you need for the 1 kg. You are trying to do it for the 1.5 kg, 2 kg, 2.5. එතකොට ඔයාට reading set එකක් මෙතන එනවා. But it is not the extension. Extension we take from the difference of the two reading. මෙතන ඉස්සෙල්ලා තිබ්බ value එක ඉස්සෙල්ලා මෙච්චර length එකක් තිබ්බ දැන් තියෙනවා මෙච්චරක්. එතකොට මේ reading එකේ මෙයා subtract කරොත් මේ extension එක එන්නේ. So you get the difference when you don't have any mass, you don't have any extension. It's 0 definitely. But when you increase to 0.5 kg, this one minus that, you get the value. When you add another 1 kg, this one minus that, you get the value. When you add that, you get the difference, you get the value. You get a value, you get a value. Like that, you are getting certain reading, certain set of reading by adding certain mass. Now understood? Right, ne? Right. Now this mass is 2.5 kg. 2.5 kg තමයි දැන් මේ tray එකේ තියෙන්නේ pan එකේ. 2.5 kg. Now what you are trying to do, you remove 0.5 kg each time. 2.5 kg තියෙනකොට you have a reading. මෙන්න මෙතන reading එකක් තියෙනවා. No problem with that. ආපහු මෙන්න මෙතනට ආවහම you may have a reading. You may have a reading because we all are taking the reading, adding and removing both instant. මෙතෙන්ට ආවහම 0.5 kg remove කරලා මෙතෙන්ට ආවම total mass now hanging is 2 kg. For that 2 kg you may have a new reading. Maybe new reading or the same reading. Same thing for 1.8. Same thing for 1 kg. Same thing for 0.5 kg. Same thing for 0. Maybe those two reading would be different. When the puluang, there must be certain reason behind that. After that, what you need to do, you need to take again the same set of reading. Subtract. You can do it by doing this. Subtract that and get the reading. Like that, you feel it. It is definitely, maybe some value is there. Maybe some values there, I don't know. Maybe some values there. So based on those two reading, for 0 kg, you may have a certain reading now. Take, add them and divide by 2. For 0.5 kg, you may have adding and removing two reading. Take that and divide by 2. You may have a reading. Like that, you get certain set of values now. Okay? I hope you could understand that. Right. Now, what you want is this axis, this column and that column only. Based on those two columns, you are going to draw a graph. Look at here how I'm going to do that. I will explain. We know that the force over area equal YE over L. Right? F equal AY E over L. Here F is the mg now. Mg AY E over L. Because we take simple M mass. Simple M mg, I will subject simple E now. Here mgl divided by AY extension equal GL over AY into simple M. You are changing simple M. It looks like X. For the system G, L, AY all are constant. You are changing simple M and based on the simple M values, you try to find the extension. Looks like the gradient. So based on that, you may get a graph like this. This is what extension versus simple M. Extension versus simple M, okay? From that gradient, let's say alpha, tan alpha equals the gradient of the graph. From that gradient, you can, let's say it is M dash, the gradient of the graph, M dash equal then GL over AY. So the Young's modulus is equal then GL over AM dash. That is how you do it. L is a measurable quantity, the length of the wire. You can measure the length of the wire at the beginning. Length you can measure. G is the data. Cross section. Cross section measure. You may take a diameter measurement. Measurement is the diameter. Three location. Take the three location and also do it for the mutual perpendicular values. Method reading for this one you get first reading. Second reading is the same location but perpendicular to the previous one. You repeat it for the three situation. You get the diameter then. Diameter. Take the average of that. So the average diameter is maintained now. So how to find the cross section? Phi r phi d by 2 square. No? Phi r square. With that we can find the cross section. M dash is the value you can take from the graph. So from that you can find the Young's modulus of steel. That is the simple story of this practical. Up to now, so far I have explained why we take adding and subtracting. Adding, add කරගෙන යනකොට reading එකක් ගන්නවා, අඩු කරගෙන යනකොට remove කරගෙන යනකොට reading එකක් ගන්නවා. මේ වලට reasons තියෙනවා. ඇයි එහෙම කරන්න කියන එක මතක තියෙන්න ඕනේ. මම ඒවා explain කරනවා one by one. ඉස්සෙල්ලාම මේ note එක පොඩ්ඩක් complete කරලා එමු. ඊට පස්සේ ඉතින් ටික කරමු. Right? Measurement of Young's modulus available in the form of wire, material and apparatus. Two uniform steel wire of length about 3 meter and diameter of 0.5 millimeter each. Both hung the same rigid support and the main scale is calibrated in millimeters and alongside a vernier scale V attached to the other wire, a pan to bear the weights, meter ruler, a micrometer screw gauge, and set of 0.5 weights. The theory. Under the theory, you need to write that. When make a theory part, take a making them complete that, and you can write up to that point, draw the graph also. To complete, tell me, the method weight to make it exactly vertical. Otherwise, like it's like a curve thing. No? It's a wire, and to make it vertical, you'd use dead weight. We call it dead weight. Done, right? Okay. Under the method, as shown in the figure, hang a dead weight, dead load, dead load from the wire P to which the main scale is attached to keep it free of bends. Hang the pan from the wire Q to which the vernier scale is attached. Observe the scale reading using the vernier and record it. Now place an initial 0.5 kg on the pan and obtain the reading on the scale again. Continue adding 0.5 kg to the load each time and obtain the corresponding scale reading for each total load. After obtaining 5-6 reading in this manner, remove the added weight in the same order of 0.5 kg each time and obtain scale reading until the load returns to its initial value. Enter all reading in the table. The table also I have given. Measure the length of the wire Q from the support up to the vernier using the meter ruler and record it. Also measure using the micrometer screw gauge the diameter of the cross section of the wire Q at 3 different places. Taking 2 readings normal to each other at every place and record the readings. Right. I will explain why I have selected not myself, but it is the practical. Why we need use 2 wires. Why we need to have 2 wires. Lamai, when you are doing, let's say we have only single wire. What make a current තිබ්බන ඕන single wire එකක් use කරලා කරන්න පුළුවන්. අපි මේකට යටින් ඕන scale එකක් use කරගන්නවා. මෙන්න මෙතන mark එකක් දාගන්නවා. හරි. මෙයා නෑ දැන්. හොඳේ? මෙයා නෑ. If there is no PQP wire, you keep a mark on that point and there is no requirement for the vernier scale. You put some certain mass 0.5 increment each time you measure the total length. Not the total length, mark plus this value. So this is the new extension E1. Again, do it 2k 1 kg, measure it length 1.5 to 2.5, like that you can do it. Instead of using a single wire, why we use two wires is important. The reason behind that, when you are doing this practical, if the temperature change in the system, let's start with 25, but when the temperature is over, when the practical is over to 35, because of the temperature change, there can be significant length in the wire. But if you are using two wires, identical wires, both are affected equally. So the main scale, vernier scale affected same distance, so no problem. Did you understand that? The one reason is that. Right? One reason is the second reason is when you are doing this practical, what happens if there's a bending part? You hang it through the ceiling. If the ceiling bend because of this weight, we don't know it is bent, but we feel that this extension which is totally wrong. So if you are using both wires affected the same way. So no problem. Am I clear? So those are two possible reasons. Please remember. Main two reasons. Just shall we check whether we have it properly? In the practical, two similar wires were used because of the following reasons. If there's a temperature variation, both wires will be affected equally. The scale readings are not affected due to temperature changes. If there's a bending of the suspension, both wires will be equally affected. Readings are independent from the change due to bending. Okay, clear. Then I need to explain why we need to take two readings by adding and removing. Look at here, I will explain that one also. The important point this practical is only applicable for which limit? Which limit? Under which limit? Proportional limit. So because the Hooke's law can apply only for the proportional limit, you can't apply Hooke's law for any other things. Neither, you can't do that. So proportional limit should maintain, right? So if you are getting a permanent extension after removing the weight also, after removing total weight, permanent extension, there must be two reasons. Permanent extension, after removing the total weight, there will be like beyond the proportional limit. That's one reason. The other reason is when you are having two different answers, I mean two different big answers different. I mean, if I explain with the table. So for example, when you take 2 kg, let's say 1 kg, think about the reading here. When you're removing and do it, you get a very large number, large value here, very large value. So that tells us the two different readings are very high. Even you feel that you get two different readings from here also, very considerable, I mean considerable difference. Right? Considerable difference එකක් වෙන්න පුළුවන්. එතකොට එහෙම වුණොත් අනිත් එක මෙතන permanent extension එක උත් ඉතුරු වෙනවා. ඒ කියන්නේ proportional limit එක exceed වෙලා තියෙන්නේ. ඒ කියන්නේ elastic limit, even it is go beyond the elastic limit, isn't it? It go beyond the elastic limit. එතකොට ඒ practical එක issue එකක් තියෙනවා. It's not the only reason. There's another reason. Sometimes these cables are like small windings are there. Small windings are there. So if you are hanging certain weight for 1 kg, this winding is still there. But when you increase to 1.5 kg, this winding is removed. Winding remove and make it straight. Right? Winding is remove and make it straight. So we need to actually, you need to know that when you are taking the average value, that error can be minimized. That's the reason. That error can be minimized. ඔයා දැන් මේක තේරෙන්න ඕනේ මෙතන මේකේ first reading එක value එකක් එනවා second reading එකට value එකක් එනවා හැබැයි මේ second reading එකේ එන value එකේ error එකක් එක්ක එන්නේ හැබැයි when you are taking the uh, when you are taking the sorry first reading is with error second reading you take the exact value because binding is not there now but when you are taking the approach you can minimize that are you clear with this everyone of you okay ne? Reason for taking two reading by adding the weight and removing the weight. To check whether the wire exceeds the proportional limit. That's the one reason. To minimize the error due to winding of the wire. Okay. Right. I have already done the section, but better to complete this part also. Right. The subtopic fatigue failure. You can use the page number 11. If I'm not mistaken, it's page number 11. Yes, page number 11. Please write fatigue failure. Fatigue failure. Fatigue failure. So, may give me a second. Right. Okay. Sorry, I got this urgent call. Right. Look at here. What is meant by fatigue failure? Fatigue failure. Let's explain this. Let's say you have a wire like this, right? Let's say you have a wire like this. When you keep on vibrating like this, when you keep on doing that, what will happen? what will happen? It will start to break. It's a breaking point. It will start to break actually by repetition, by repeating the same load. We call it cyclic load. You can break this kind of thing. It's called the fatigue failure. Actually, when you apply a repetition now, I mean, when you repeat the certain load, what will happen? Let's say initially this is your graph. This is your graph. When you repeating that, what will happen? This particular graph change to this breaking load change to very small value. It's called the fatigue failure. When you do the repeating, when you're repeating the same load, cyclic, we call it cyclic load. When you're doing same load, you can reduce the breaking load. For example, if it is normal situation, you can break like 200 Newton, 200 Newton, no 200 Newton per meter squared. If you go with the stress, you can do it like 100. If you do it like fatigue, you can do it like repetition, the same force over and over again. You can take that breaking load to a very small value. Right? By knowing or not knowing, you are doing this section. Even your parents are doing these sections. They don't have much idea, but they are doing this kind of thing and break this wire. That's called the practical situation. Theoretically, this is the point. We can drop the breaking load to a very small number. Right. I will give few examples. I can give plenty of examples because we all are like, so we all are in the industry. We can give you plenty of example, but only thing is it takes certain time. I mean, like sometimes we feel that time wasting. But remember, it's not a time wasting. You get some practical knowledge with this. Haven't you seen that sometime the railway tracks are removed time to time? Railway tracks are like it's outside the normal route. They replace the railway tracks. Periodically, they are doing that. The people are scolding these people are like making money. මිනිසුන් බයිනවා ඉංජිනේරු හොරු මේ උන්ට මේකෙන් ගාණක් හම්බ වෙනවා මේ හොඳට තියෙන රේල් පාර ගලවලා අලුත් ඒවා දා ගන්නවා ඒතකොට ගාණක් හම්බ වෙනවා කමිෂන් හම්බ වෙනවා කියලා. ඕක නෙමෙයි එතන තියෙන දේ. ඕක නෙමෙයි එතන තියෙන දේ. ඔයාලා දැනගන්න ඕන ඔයාලට දෙයක් තේරෙන කට්ටිය මිනිස්සු කියන හැම එකම තේරුම් ගන්න එපා වැරදි විදියට. ඕක නෙමෙයි එතන පොයින්ට් එක. රේල්වේ ට්‍රැක් එකක ට්‍රේන් එක හැමතිස්සෙම යනකොට මොකද වෙන්නේ මේ රේල්වේ ට්‍රැක් එක සයික්ලික් ලෝඩ් එකක් හැමතිස්සෙම වෙනවා රේල්වේ ට්‍රැක් එකට රේල් පීල් එකට මම කියන්නේ රේල්වේ ට්‍රැක් එකට හැමතිස්සෙම සයික්ලික් ලෝඩ් එකක් එනවා ඒක අපි රිප්ලේස් කරන්න ඕන පීරියොඩිකලි රිප්ලේස් නොකරොත් මොකද්ද වෙන්නේ what will happen if you are not doing that if you are not doing that even a small load there will be a fatigue failure in this railway track what will happen then what will happen the people will die no there will be a disaster the people don't know and scold these people they are like making money සල්ලි හම්බ කරන්න නෙමෙයි ඒක කරන්නේ ඒක කරන්න ඕන නිසා ඕකෙන් කවුරු සාප්පුවේ දාන් කරන් යන්නේ නැහැ රේල් පිල්ලක් වගේ සාප්පුවේ දාන් කරන්න පුළුවන් බෑනේ ඒක එළිය දැම්මයි කියලා අවුලකුත් නැහැ ඒක නිසා මිනිස්සු බයිනවා මිනිස්සු දන්නේ නැහැනේ මිනිස්සු බයිනවා මුන්ට මේකෙන් ගාණක් හම්බ වෙනවා මේ හැම පාරම මාරු කරන්නේ මේක තමයි ඒක නෙමෙයි රීසන් එක රීසන් එක අරකයි ඒ කියන්නේ රේල්වේ ට්‍රැක් එකක ට්‍රේන් එක යනකොට හැමතිස්සෙම ඔයාලා දකිනවා මේ රේල්වේ ට්‍රැක් එකේ යනකොට මෙහෙම ভাইබ්‍රේෂන් එකකුත් වෙනවා ට්‍රැක් එකේ හැමතිස්සෙම because it's a massive mass no එතකොට because it keep on a kind of metal the concrete layer on top of a concrete layer maybe concrete or timber those days we had timber now it's concrete most of the layers so always like vibrating like this so at this kind of point there will be a fatigue failure එකක් වෙන්න පුළුවන් fatigue failure එකක් වුණොත් වැඩේ අනාතයි ඒක නිසා replace කරන්න ඕනේ right we call it periodic maintenance preventive maintenance we call it preventive maintenance we need to do preventive maintenance දැන් ඔය Moratuwa power plant එකේ preventive maintenance කරනවා time to time unfortunately it is the biggest power plant in Sri Lanka. Very difficult to take that, I mean, outage. The reason is because it's continuous run. When we are taking that for the maintenance purpose, the people are scolding these people are getting, these engineers are getting money from somewhere else. Maybe they are trying to take money. The people don't know. That's the main reason. In a country like Sri Lanka, most of the people are like they don't think anything. They just hear what the other people think, what the other people says, and they started to go along that track. This is how these things are happening in Sri Lanka. So ඔයාලා එහෙම වෙන්න එපා. ඔයාලට දෙයක් තේරෙන කට්ටිය ඉගෙන ගන්න එකේ වටිනාකම තේරෙන්න ඕන. Especially when you are doing a physics subject, you get that analytical skill. ඔයා physics උත් ඉගෙනගෙන අර නිකන් අර හැමෝම කරන එක කරන්න එපා. ඒක වැඩක් නැති ඔයාලකට. ඔයාලා දෙයක් subject එකක් මේකෙන් ඔයා ඉගෙන ගන්න ඕනේ මේක ටිකක් වෙනස් subject එකක් නේ. එතකොට ඒකත් ඉගෙනගෙන ඔයත් කරන්නේ අර normally කරන කෙනෙක්ම නම් වැඩක් නෑ. ඔයා හැමතිස්සෙම analyze කරන්න පුරුදු වෙන්න ඕනේ. ඇනලයිස් කරලා බලන්න ඕනේ මේ කියන එක ඇත්තක්ද කියලා. right? දැන් මේ දවස්වල ඇනලයිස් කරන්න යන්න එපා. හුඟක් ඒවා සමාජයේ තියෙන මොකද වෙලාවක් නෑ ඇනලයිස් කරන්න. You have your own work, right? ඒ නිසා ඔයා ඇනලයිස් කරගෙන ඔයා ඒ ටික කරගන්න. මේ දවස්වල ඇනලයිස් කරන්න ගත්තොත් එහෙම අනාථ වෙනවා. මොකද ටයිම් එක ලිමිටඩ් නිසා. එක්සෑම් එකෙන් ඉවරලා වැඩක් නැති වෙලාවකට පොඩ්ඩක් බලන්න මොකද්ද මේ රටේ උත්තේ වෙන්න කියලා. මේ දවස්වල දිගටම අර මිනිස්සෙක් මරපු එකක් ගැන තමයි දිගටම කතා වෙන්නේ. නිවුස් බලන්න ඒක හරිම අප්සෙට් වැඩක්. නමුත් ඒක තමයි දිගටම කතා වෙන්නේ රටේ මේන් නිවුස් එක සංජීව. right? right. ඒවා කියන හදන්න වාට ඒකයි වා ඇනලයිස් කරන්න ඕනේ. නැත්තම් බෑ. හැමකටම රීසන් එකක් තියෙනවා. මාරු කරන්නේ නෑ මිනිස්සු කියන්නේ. එහෙම ඉතින් එක්සෙප්ෂනල් කේසස් ඇති. දැන් ඔය solar සම්බන්ධව ගත්තොතින් I don't like to talk on solar part. solar ගත්තොතින් ඕකේ ඇත්තටම ඉන්ජිනියර්ස්ලා කිව්වා CBK ඉන්ජිනියර්ස්ලා ඒ කියන්නේ ගහන්න පුළුවන් ලිමිට් එකක් තියෙනවා. ගහන්න පුළුවන් ලිමිට් එක එක්සීඩ් වුණොත් සිස්ටම් එක අන්ස්ටේබල්. ඒ කියන්නේ සිස්ටම් එකට ඇබ්සෝබ් කරන්න පුළුවන් ප්‍රමාණයක් තියෙනවා. ඒක කිව්වහම පිට මිනිස්සු කියන්නේ solar වලින් මිනිස්සුන්ට සල්ලි හම්බ වෙන්නේ නැහැ, ඉන්ජිනියර්ස්ලා සල්ලි හම්බ වෙන්නේ නැහැ. හරිම මෝඩ විදියට ගුන් කතා කියන මිනිස්සු තමයි බහුතරයක් ලංකාවේ ඉන්නේ. ඉතින් ඒක නිසා කතා කරනට වඩා හොඳයි නොකර ඉන්න එක. ඊට වඩා මෙතන උනත් කතා කරනට වඩා හොඳයි නොකර ඉන්න එක මට හිතෙනවා. ඒ කියන්නේ ගහන්න පුළුවන්. ඒ කියන්නේ සෝලර් කියන එක මේ වගේ සිස්ටම් එකක් අපේ සිස්ටම් එකට මේකේ ගහන්න පුළුවන් ලිමිට් එකක් තියෙනවා. ඒක එක්සීඩ් වෙන්න ගහුවොතින් එහෙම ඔය වගේ ප්‍රශ්න වෙනවා. දැන් එකපාරක් සන්ඩේ බ්ලැක් අවුට් එකක් උනේ. ඒ වගේ ඉෂුස් එනවා. ඒක ඉතින් ඔයාලට එක්ස්ප්ලেইন කරන්න පුළුවනි යම් වෙලාවක් අරගෙන in a day if the time permit I will do it, but I don't have any idea to explain it again in this class. I think I explained it for 2026 A-level students. If the time permit I will do it for you. ඔයා දැනගන්න මේ මේකේ තියෙන සිටුේෂන් එක මේ වගේ එකක් කියලා. ඒක නිකන් කිව්වට තේරුම් ගන්න එපා. ඔගේ මෙහෙමයි. දැන් ඔගේ සමහර පුද්ගලයෝ ඇති ඕනම තැනක ඉන්නවනේ මිනිස්සු. කියන්නේ හොරගම් කරන මිනිස්සුත් ඇති ඕන අපි දන්නේ නැහැ. ඉතින් මේ එහෙම කියන්න බෑ අපි දන්නේ නැහැ. එහෙමත් ඇති. හැබැයි සියල්ල හොරු කියන එක වැරදි. ඒකයි මම කියන්නේ. right, okay, let's move to fatigue failure. I will give another example. I don't know whether you have seen that. මෙන්න මේ වගේ එකක්. Have you seen that in a high tension line? In a high tension line, the high tension tower line, let's say this is the tower line, the cross arms are there, there's the high tension line, the line comes to this point and it is connected to the next tower using certain insulators. At this point a small gadget is there. Haven't you seen that? මෙන්න මෙතන පොඩි gadget එකක් තියෙනවා. Right? I think you haven't seen that. Okay, I will, if the time permit, I will send you a photo on this. right? I will send you a photo, then you could see this one. Definitely you could see that, but you don't remember because we are not purposely looking at that now. The insulators like that, it's connected with the insulator to the tower, and this point you have this called the vibrational dampers, right? Let's say it is not there, this is not there, right? The high tension line is something like 1 kilometer, maybe like let's say 800 meters. So if there's a wind, if the wind blows, what will happen? They start to vibrate like this now. This wire start to vibrate like this. If the wind is always there, if we start to vibrate like this, what will happen? What will happen? What will happen at this point? There's a fatigue failure. There's a fatigue failure. There will be a disaster. We are a makeup there will be a disaster. Right? එතකොට මෙතන fatigue failure එකක් වෙන්න පුළුවන්. Fatigue failure, if there is a fatigue failure, definitely this will jump to the ground. Right? Maybe there will be a disaster. Right? In a 220 line, 132 kV line, if it's broken and jump into the place where the people live, there will be a disaster. Right? So in this particular case, a device called vibrational dampers is there. The vibrational dampers absorb that and stop that vibration. It absorbs that. It absorbs that. Because of the vibrational dampers, the fatigue failure is avoided. That's the reason. Right? Okay, just write under that fatigue failure. Fatigue failure is the formation. Fatigue failure is the formation and propagation of cracks. Formation and propagation of cracks. Propagation of cracks due to a repetition of repetition or cyclic loads. Repetition or cyclic loads. Repetition or cyclic loads. Right. I think you have heard that something called the vulcanized rubber. Have you heard that vulcanized rubber? Right. Vulcanized rubber, if you started to draw how the force versus the extension develop, it is something like this. This kind of graph could obtain. This is not a like linear proportional thing. It goes like this and turn back and come along this line. I will explain this, what is happening. Right? If you check the area under this curve, this tells you when there is extension, the work done. The work done. When a area, when making cover when area, the work done. Right? If you take this area, this tells you what is the energy release when it comes to normal position. Make a vulcanized rubber, if you increase the length, the energy is deposited. When you release the force, it comes to the original length and the energy would release. Clear? Okay. But only thing is, when it comes to original length, the energy that absorbed is not given as the energy release. Won't you feel there is an issue? The energy which provided is not provided again. I mean, energy that we provided to give the extension would not give again to the system, outside the system. The energy absorbed here, energy return. So there's a small issue. That could observe in a vulcanized rubber or simply rubber. I will give you a small example. Imagine the long jump. Imagine the long jump, a game like long jump. If you are jump from this to the what you call the what is that whatever the thing the rubber, it's like a rubber bed. No, what is that? I don't remember the name. If you jump, let's say the jump, long jump, මෙන්න මෙතන තියෙනවා වාගේ බෙඩ් එක මෙට් එක රබර් මෙට් එක ඕකේ මෙතනින් ඇවිල්ලා මෙහෙම පැනලා මේක උඩට තමයි වැටෙන්නේ දැන් මෙයා මෙන්න මෙච්චර උසක ඉඳලා තමයි මෙතෙන්ට වැටෙන්නේ දැන් මේ මිනිස්සයා මෙතෙන්ට උස්සනවා දාපුවා වැටෙන්න පස්සේ ආයේ උඩට ගන්න මෙතෙන්ට නෑනේ එතෙන්ට එන්නේ නෑ එයා මෙන්න මේ වගේ ප්‍රමාණයක් තමයි එන්නේ මේ වගේ ප්‍රමාණයක් ඇවිල්ලා ආයෙ මෙතෙන්ට වැටෙනවා ආයෙ මෙතනින් අඩු වෙගෙන යනවා if it returns the same energy that it absorbs, you can understand it definitely comes to the same position. Someone need to catch him. Otherwise, he can't stop this jumping. Someone need to catch him while it is jumping like this. So vulcanized rubber, inside this rubber bed, what happening? Actual scenario is while it is absorbing the energy, it keeps some amount of energy as heat. This energy, this amount of energy is heat. We call it hysteresis loop. අපි මේකට කියනවා hysteresis loop එකක් කියලා. It absorbs that energy as a heat. If you can understand, when you increase this length of this rubber band and release it, you will feel that the small temperature rise is there. Very small temperature rise is there. මෙයාව පොඩ්ඩක් දිග length එක වැඩි කරලා right දිග length එක ටිකක් වැඩි කරලා මෙයාව normal length එකට ගත්තාම මේක touch කරලා බැලුවොත් you feel that there's a temperature rise. That is because of this. The rubber behave like that. In a question, they would give you, assume the rubber behave like a Hooke's law. Under the Hooke's law, you can take the normal way that we discussed earlier. Otherwise, you can't take that. Which is called the hysteresis loop. We call it hysteresis loop. Right? This is the loading situation. This is the loading. This is the loading and this is unloading. Loading and unloading. Write a topic, hysteresis loop. The force extension graph. The force extension graph for rubber shows that force extension graph for rubber shows that the behavior as the load is removed, the behavior as the load is removed is not same as that when the load is being increased. This is called hysteresis. Hysteresis. This is called hysteresis. And the curves are said to be, and the curves are said to make, and the curves are said to make, and the curves are said to make hysteresis loop. Hysteresis loop under force. Under a force. It is shown that it is shown that the energy absorbed it is shown that the energy absorbed it is shown that the energy absorbed by a material by a material by a material by a material is represented by between these two curves. Energy absorbed between these two curves. Right, done. Eh? Can you write within bracket hysteresis loop? Hysteresis loop. Question number 5. Question number 5 in your tutorial. It's a part of the question. Question number 5. Right. Right, let's see the past of the question. The figure shows force extension graph for a rubber band. Consider the following statement. The rubber band does not return to its original length after stretching. Yes. For this one, yes. Okay. There's a small extension, permanent deformation. The magnitude of the total work done during the increase of length is less than the magnitude of the total work done during the decrease of the length. The magnitude of the total work done during the increase of the length is less than the magnitude of the work. What you can say about that? False or correct? It's a false statement. How about the other students? You'll agree with this? Yes or no? It must be higher. Is that clear, one of you? Yes or no? Right. Heat can be generated in this process. Yes, that is true. The number 4 is the answer for this question. Number 4 is the answer. Right. Let's move to question number 20. Let's move to question number 20. Question number 20. The diameter of an elastic wire of length 5 meter is 1 millimeter if its length increased by 0.1%. Actually, they are giving you the strain. Strain for 100, it is 0.1. As a percentage, it gives you, right? 0.1. For 100, it is 0.1. That is what we call strain. Okay. Young's modulus of the Y also given 2 10 to the power 11. They want you to find the force applied. The diameter of the elastic Y also given. The length also given. The force applied, calculate the force applied. Calculate the work done. Sorry, the work done. Did you get the answer, every one of you? I told you to do 20, right? Oh, no. Yeah, 20, right? Right, okay. Let's do it. Calculate the work done. When it comes to work must be equal to half FE. Half FE. That's the work done. Here, extension over L must be equal to F strain. Extension equal 0.1 divided by 100 into length, which is 5 meter, which is 0.5 into 10 to the power minus 2 meter. E equal 5 10 to the power minus 3 meter. That's the extension. Strain equal Young's modulus into strain. Young's modulus also 2 10 to the power 11. Strain 0.1 divided by 100. It is 2 divided by 10 to the power 8 Newton per meter squared. That's the answer for the strain. Stress. F over A equal stress. F equal then cross section 5r squared 5.1 divided by 2 diameter is given minus 3 5r squared into 5r squared into what? 5r squared into this answer. F equal 5, it is 22 over 7. 0.1 divided by 1 multiplied by minus 2. We can say 0.5. So the 5 multiplied by 10 to the power minus 5, then take the square of that into sigma. Make up a half 0.5 0.5 5. Yeah, this is the answer then. F equal 22 over 7. 25 10 to the power minus 10 sigma 2 10 to the power 8. Just substitute these values. Half force, it is 22 over 7. 25 2 10 to the power minus 2, extension 5 10 to the power minus 3, extension 5 10 to the power minus 3. This is 11 into 50, 5 10 to the power minus 5 divided by 7. What is that value? Three nine two 10 to the power minus 5 joules. That's the work done. 3.92 10 to the power minus 3 joules. 3.92. This is a small issue. It must be, maybe it is 392. 392. Did you get the answer, any one of you, the work done? Yes or no? Right, okay. Right. Right. Do you have anything to ask up to now? I mean, I have completed the theory section. I request you all to go through these questions. You can try now question number 1 to 1 to 31. 1 ඉඳලා 31 වෙනකන් try කරන්න පුළුවන්. මම questions feedback කළා. නමුත් it is not enough. We need to discuss all the questions. ඔයාලා try කරන්න. I have done everything under the theory section and discuss what is required to do questions. I know that it is not easy task. ඔයා කරන්න හැදුවම ඔයාලට මේක එක issue සේවි. For example, ඔයාගේ cross section එක මෙහෙම solid නොවෙනකොට, let's say you are keeping certain object on top of that, on top of this cylinder. The cylinder is not solid one. එතන cross section එක ගන්නකොට solid section එක විතරයි ගන්න ඕන. අන්න ඒ වගේ ටිකක් කර තියෙනවා පොඩි questions වගේ ඔයාලා try කරන්න. Anyway, we have almost done. The section is completed, fully completed. Only thing is now you need to practice what you have done. How to practice? By doing questions. දැන් ඕක හොඳටම තේරෙනවා ඔයාලා try කරලා මම next එකේ කරනකොට. try කරනකොට සමහර වෙලාවට පුළුවන් වේවි, සමහර වෙලාවට බැරි වේවි. හැබැයි 1 ඉඳලා 31 වෙනකම්ම කරන්න. 1 ඉඳලා අපි කරපු ඒවා skip කරලා 31 වෙනකම්ම කරන්න. ටිකක් පොඩ්ඩක් දවසක් වැඩිපුර මහන්සි වෙන්න වෙනවා. රැයක් වැඩිපුර මහන්සි වෙන්න වෙනවා. පොඩි වෙලාවක්, ඒ කියන්නේ ඔයා වෙලාවල් කීපයක් සෙට් කරගෙන කරලා දාන්න. කරොතින් ඔයාට හොඳටම තේරෙවි ඔයාට මේ lesson එක හරි ලේසි වෙනවා කියලා. මම මේකේ difficult questions discuss කරලා ඉවර කරනවා next week එකේ. I'll be starting the new topic also, viscosity. එතකොට ඔයාලගේ පැත්තෙන් help කරන්න ඕනේ මේ ටික කරයි යන්න. මේක සරල නැහැ, ටිකක් අමාරුයි. Even it is difficult for you all, I know that, because you all are having several classes now. But don't give up that. If you do it, it is for you. පොඩක් මහන්සි වෙන්න, ඒ කියන්නේ වැඩිපුර මහන්සි වෙන්න මේ කාලෙදී. ඒ කියන්නේ වෙනදා 10ට නිදාගෙන, even if you wake up like 5 p.m, maybe you may not like that, but if you can increase that time, but if you can increase that to like 12 p.m 12 p.m to like 4 p.m, like there are only few days, only for a few days to complete this contents. Take 2-3 days, then you can complete these questions. Don't give up. කරලා දාන්න. skip කරන්න එපා. කරතින් ඔයාට theory කොච්චර improve වෙනවද කියලා. Right? How you feel that is today is okay? How the content is okay with you? So how about the other students? You all are okay with what we discussed up to now so far? Right. The wala in a way you need to be happy. The reason is you have completed 1/3 of the lesson. ඉතින් ඕක හොඳටම කරන්න නම් ඕක හොඳටම fluent කරගන්න ඕනේ. Fluent කරගන්න නම් මොකද්ද කරන්න ඕනේ? There are 31 questions. Do it. That's all. ඒකයි මේකේ point එක. දැන් මේකේ මම ඔයාට ඕන knowledge එක දීලා තියෙනවා. හැබැයි knowledge එක තිබ්බට එක එක තැන්වල තියෙන්නේ. ඒ knowledge එක ඔයාට use කරලා questions කරන්න ගත්තාම තමයි ඔයාට හොඳට මේ subject එක clear වෙන්නේ. ඉතින් ඒකට මම questions කළා හරියන්නේ නැහැ නේ. දැන් මම මේකේ 1 ඉඳලා 31 වෙනකම් questions කරාට ඔයාට පුළුවන් වෙන්නේ නැහැ නේ. ඔයාලා ලිබ් බලාගෙන ලියන එක. එහෙම නෙමෙයි. ඔයා try කරන්න ඕනේ. You try, then I'll be discussing the next week. I'm giving you the time now. I'll be giving you like 7 days to complete this 31 questions. How to do this one? You need to do extra work because otherwise you can't complete this section. 31 means in terms of days, 7 days, let's say 6 days, only 5 questions you need to do per day. Questions පහක් කරන්න දවසකට. පොඩි questions ටිකක් වැඩිපුර කරන්න. එතකොට ලොකු questions වලට වෙලා ඉතුරු වෙනවා. එකපාර ලොකු questions වලට drop වෙන්න එපා. පොඩි questions කරලා practice කරගන්න. ඔයාට equations ටික fluent වෙන්න ඕනේ. equations use කරන හැටි තේරෙන්න ඕන. අන්න ඒ වගේ කාරණා ටිකක් ඕකේ තියෙනවා දරුවෝ. ඒ නිසා ඔයාලගේ පැත්තෙන් you need to do simple question first, then go to the difficult questions. In my tutorial, the first few questions are not so difficult to get familiarized with the equations. I have given those questions, so better go with that. The MCQs you can start them. The only 31 questions. If you do that 31, I will be guaranteed you can definitely do the question which will be given at the exam under the elasticity. So what a confidence එක අපි දෙනවා. ඒක ඔයා තමයි කරන්නේ. ඔයා දැන් next week එකේ when I do the questions, if you look at that and just writing that, nothing would happen. හරි කිසි දෙයක් වෙන්නේ නැහැ. ඔයා හිතනවා ඔයාගේ බුද්ධිය වර්ධනය වෙන්නේ නැහැ. There are no rocket science. ඔයාගේ බුද්ධිය වර්ධනය වෙන්නේ නැහැ මං කලයි කියලා ඔයා තමයි කරන්න ඕනේ. ඔයාගේ ඇඟිලි වල කුරුක් මහත් වෙන එක තමයි වෙන්නේ. ඔයාගේ brain එක development එකක් වෙන්නේ නැහැ මේ subject එකේ. ඒ නිසා ඔයා try කරන්න ඕනේ. මම ඇත්තටම කියන්නේ you need to try yourself, otherwise it is pointless. If you feel that by looking at these questions you get certain knowledge, no, it's not that. You try, then we'll discuss. Okay, that's all for today. Now the time is 12:40. I have another class at 1:30, right? But I can manage. But anyway, if you have anything, you can ask me. If not, we will meet again on through the again Tuesday. Yeah, again Tuesday in a normal class. We will be discussing. There is a few requests from few students to discuss the MCQs under the optics section. So I'll sort of giving those discussing those MCQs with you to revise as a revision for the MCQs. I mean MCQ section and few questions. We will do that on Tuesday class. Again, we'll start the paper class again Saturday. Okay, we'll meet again on next week, right? හොඳට මහන්සිලා වැඩ කරන්න try කරන්න. Okay, thanks for joining the live class. For those who join the reverse class, you can watch the recording also, but I request you to be on the live class. Okay, we'll meet again on next day.